Hello and welcome to the second lesson in what will be an extensive series covering various different C++ examples. And today I would like to begin this lesson by slightly modifying the list of examples that I'm going to be demonstrating in this video series. Now, if you didn't watch the last lesson, I basically talked through various different examples I'm going to be taking the viewers through, and those examples will be extracted from various different books I've read. And one of the books I've read is called The C++ Programming Language by Jean Stroustrup, and I noted various different examples within the context of that book that I would like to take the viewer through. And I would like to slightly modify that because I actually looked through that book once again, and I found a couple more different examples that I would like to take the viewer through. So just to slightly modify the list I outlined in the last lesson, I don't know if I explicitly denoted the fact that these particular examples came from this particular book, but nevertheless I will proceed to outline the various different examples within the context of that book I would like to demonstrate. And the first is a string implementation, the second is a vector implementation, the third is a tuple implementation, the fourth is a desk calculator, which is a program located on page 241, I believe, and we also have a matrix implementation. Now that's not in the specific order that I'm going to be walking through those examples. I still have to work out the order that I'll be doing those particular videos on. Now, a secondary point relating to this book is that I'm going to write a paper relating to an overview of the C++ language and present it in a lesson. And one of the things I would like to include within that paper is a generalized model that encapsulates the structure of all possible C++ programs. In other words, write a paper that details the characteristics of all possible C++ programs such that you can use that generalized material in order to understand any C++ program that may be presented to you. Now again, it's not ideal because you're not going to gain a sophisticated understanding of how the different facilities work and so on, and so consequently you won't be able to necessarily understand what I call the logical foundations of various different C++ programs that one might present to you. But nevertheless, that's the goal of the paper, and then a sub-paper within the context of that paper detailing the type system. And the type system in C++ is what I would call a robust and logically contained system. And I would like to write a sub-paper detailing the type system. And this paper will be based off of the presentation located within the context of the C++ programming language by Jean Stroustrup. But I'm not going to copy it. I think the word is verbatim. I'm not going to copy it word for word, metaphorically speaking. I'm going to make sure that the paper is original. So in other words, it's going to be my particular spin on what I think the C++ programming language is. Now there are a few things that I would like to outline before we begin today's lesson, and that is the following. The first point is this. The point of these videos for me is not only to teach various different concepts, but to challenge myself, and so to that end, I'm obviously preparing for these lessons, but I'm only constructing a minimal document relating to the general structure of the lesson. And so consequently I would say the following, and this is important, and I outlined this in the previous lesson, but I will state it again. I am guided by a minimal amount of notes. Consequently, remember these 3 points. I may forget some things. In other words, as a consequence of the fact that I would like to challenge myself, and that's the whole point of this, alongside the idea of teaching, I may, because I have the examples where the books from where the examples are extracted beside me just in case, and also to actually have access to the source code instead of having to write it out. But I'm only going to use that if absolutely necessary, and so consequently I may forget some things. That's the first point. The second point is I may make some mistakes. And the third point is, even though I may forget some things and I may make some mistakes, most of the concepts that will be discussed will be accurate. And in my view, whenever you're learning the C++ programming language, the most important thing, the thing of importance in my view, is that the most important thing that you do or that you need to do, is to understand the general concepts relating to different library facilities, language facilities, and so on. You don't have to remember every specific detail about a particular language facility, because it's not necessary and quite frankly impractical. And so consequently, so long as you understand the general concepts relating to the primary language facilities and so on, that's the fundamental thing of importance. And also, I forgot to, before I forget, I would like to say that in the last lesson there was significant lag issues, and the lag issues will be fixed for this lesson. Now, I think that the video quality is sufficient, but just to be accurate, for the sake of it, I suppose, it will be recorded at 10 frames per second. But I think that's sufficient because, as I will demonstrate now, I will write a word. Oh, that was a bit of lag. 1 second. I will write a word, and as you can see, it does seem a little bit choppy in terms of the video produced, but it's sufficient in my view. So with that introduction, let us begin the lesson. Let's get into some substance relating to today's lesson. So let's begin by discussing the following ideas. So the central task of programming is to express solutions to specified problems. Thus, we first identify some problem and begin formulating a program that can solve it. And so the question becomes, how do we implement the solution that will actually result in desirable behavior such that it produces results in accordance with what we would expect and require? There are perhaps various answers to this question. However, in our approach, we will consider the following points. And the first point is this: identify what the program must do in clear terms. In other words, in plain English, identify what problem the program is attempting to solve and therefore what it must do. And the second point is carefully construct a logical structure that provides the behavior we need and consequently implement the services required by the structure to form what we call an algorithm. We will discuss this term shortly. By logical structure, we mean a series of statements organized in the appropriate manner, written in clear terms that, in their totality, specify exactly how we do something and therefore what we are doing. In relation to this last point, consider the following analogy. In other words, relating to that second point that I just outlined, how can I put this in a way that is relatable to most people? And so, in order to do that, I have constructed the following analogy. It's a very simple analogy that most people will obviously be able to understand, and it is as follows. Jim has identified a problem. That problem is that he wishes to make a sandwich. Before he can do this, that is, before he can implement the solution, and that's the terminology we'll use, he must state to himself in clear terms how exactly he will go about the task of constructing a sandwich. And so he carefully considers this and comes up with the following proposal. Point number 1, get bread. Point number 2, butter bread. Point number 3, place chicken in bread. And point number 4, connect the pieces of bread. It seems like a rather strange and very simplified example, but it nevertheless powerfully demonstrates the importance, or it powerfully demonstrates the process relating to the second point outlined previously. And so now Jim can go about the task of successfully making a sandwich. Observe, however, the following point about the previous algorithm we constructed, and that's what we will refer to it as, an algorithm, and we'll get on to consider what we mean by the term algorithm in a moment, at least in terms of my take on it. So, observe, however, the following point about the previous algorithm we constructed. It is abstract in the sense that each point considered actually consists of a series of instructions in and of themselves. We refer to this as a higher level abstraction. We will return to discuss this relatively shortly. So let's discuss what we mean by the term algorithm. Now, relating to our use of the term algorithm, what do we mean by it? After careful consideration, we construct the following definition. Algorithm, a specification of a series of instructions executed in a sequential order. Note, this definition applies to single-threaded applications. Now, one may be satisfied with this definition, but others may not. The problem is that the statement is too general and permissive, and the term algorithm, at least in popular culture, implies a degree of specialization. If we adhere to this definition, then any program can be considered an algorithm. This seems unjustified. However, the definition most certainly applies to at the very least a subset of the characteristics exhibited by functions with which we associate the term algorithm. And so any definition modification would just constrain the things that the term applies to and not cause modification of the definition itself. But to be entirely honest, one second, I just dropped something. But to be entirely honest, the distinction for the present moment is irrelevant and thus need not concern us. The point at hand is that we must devise a series of steps written in clear terms that solve some specified problem. And in terms of doing that, that is a skill that you acquire through extensive experience and practice. So, what is this lesson about? What is the substance of this lesson? What problem are we initially going to try and address? And before I proceed in relation to this matter, this example is slightly more complex than the previous lesson. And in particular, this lesson will detail two implementations that solve two distinct but related problems. They're intimately related but nevertheless distinct. To simplify, we wish to implement a solution that solves the following problem. We wish to write a program that can query the contents of a file for a given word. The result of the query should be the amount of times the word appears and a list of the lines that the word appears on. So, we have specified the problem and now we must solve it. In order to do this, we refer back to our second point relating to solution implementation. That is, we carefully consider what steps must be taken to solve the problem, and when we do this, we more or less come to the following conclusion. So, we undertake that process of carefully considering in clear terms, in other words, written in plain English, the series of logical steps that need to be undertaken in order to solve some specified problem. And when we do that, we arrive at the following conclusion more or less. First, the program reads input. It reads an input file, and when it does that, the program has to implement some logic in order to remember the lines on which each word appears. And so, analyzing that particular logical service in and of itself leads to the following conclusion. The program must read the input a line at a time and take that input and break up the lines in the input file into separate words. In order to achieve that logical objective, that's what we need to do. And the second point is that whenever the program generates output, the program must be able to obtain the set of line numbers, and I use that term set in the abstract and general sense. We're not referring to the set facility provided by the standard library. The program must be able to obtain the set of line numbers associated with a given word. Those line numbers must appear in ascending order with no duplicates, and the program must be able to print the text appearing in the input file at a given line number. So, relating to the second point in our previous considerations, we have outlined in a general and abstract sense the logical steps that need to be taken in order to obtain program behavior that solves the problem we specified earlier. And so, consequently, we need to take that specification and the requirements implicit in that specification and identify the various different language facilities and standard library facilities that can provide the behavior that we need in order to solve the problem. And so we'll get on to discuss that momentarily. So in terms of our solution, what we want to do is we want to create a class. The first thing that we want to do is we want to utilize the abstraction mechanisms in order to encapsulate complexity. And so in other words, we're going to undertake an object-oriented approach to this problem. So that's the first point. The use of abstractions to encapsulate complexity. And in relation to that, in our solution, in our implementation, what we're going to do is we're going to create a class that makes querying the file easy. So that's the first point. And the second point is, and that class in and of itself will have a particular representation and a query operation. And that query operation in and of itself will return multiple pieces of information. And so the most common mechanism for returning multiple pieces of information in a single return statement is to encapsulate those pieces of information inside the context of a particular class instance. That is the simplest way to achieve that particular objective. And so consequently, in our implementation, we will be devising a custom class that can encapsulate all the information we need to return from that query operation. Now, here's the critical thing. In terms of how the abstraction will be implemented, the implementation of the abstraction relating to encapsulating the logic necessary in order to make querying the contents of a file easy, in relation to that, we're going to have to employ some logic within its implementation to perform the necessary actions and build up what we call a lookup map. In other words, as specified in our specification outlined previously, we need to undertake the action of reading a file, for instance a .txt file, and recording the amount of times each word within that file appears in the entire file. And we need to remember all that information and store it in a way that's easily obtainable in terms of being able to retrieve that information. And so consequently, the implementation of this abstraction will employ logic that can achieve that objective. And to put it simply, and again we will outline the implementation in clear terms relatively shortly, but in order to achieve that, the implementation will essentially construct a map. And a map is a standard library facility, a facility provided by the standard library, and a map is able to associate one type, an object of a particular type, with an object of another particular type. And there are complexities in terms of the way that subscripting works on map instances. For instance, whenever you subscript a map, not an unordered map, but a regular map, and that element doesn't exist, then it will automatically insert an element with a value equivalent to the value of the index, and then it will value initialize the value to which it maps in the abstract and general sense. And so in our implementation, what we're going to do is we're essentially going to construct a map that enables us to associate a string, in other words a word, with a set. And we can use this term in the abstract and general sense, but also in the technical sense, because we will be employing the use of a set, the set abstraction. We associate each string in the input file with a particular set, and that set will contain a series of integral values that indicate the lines on which that word appears. And then what we do is in the context of that abstraction, we provide a query operation that enables us to obtain the information that we need relating to a particular word. Now we have to be careful because we can't use the normal index operator. We can't use the normal index operator because that will unilaterally insert an element with the value of the index into the representation of the map, and so consequently we can't use the index operator because it doesn't conform to what we would expect. For instance, when we're talking about a built-in array and so on. And so that's the first point. Now, the reason that I'm discussing this is that the reason that I'm outlining these particular points is because the result of the query operation, which will be a member function of the abstraction, the result of that query operation will be an object of a particular class type, a custom class type that we'll devise. We'll call it query result. And the query result is intended to represent the result of a particular query. And that query in and of itself contains multiple pieces of information. That information includes the set of line numbers associated with a given word and the corresponding lines of text in the input file. Now here's the key observation. That information and that data is stored in objects of the abstraction that we're discussing, and that abstraction will be called TextQuery. And so consequently, we need to devise a mechanism to enable access to that particular representation. And so one approach we could do is we could copy the representation, but that could be very expensive, particularly as it relates to the contents of the entire file, because the file could be quite large. The second point is that we could use iterators, but the problem with iterators is that we can't synchronize the lifetime of the text query instance and the query result instance in such a manner so as to make it harmonic, in the sense that the iterators will not become invalid, and so consequently we need another approach. And in our approach, we're going to be using a facility called shared PTR. It's a shared pointer. And we'll be discussing the various different complexities relating to the shared pointer abstraction throughout this lesson, but we will discuss the basic mechanisms underlying its implementation. The shared pointer mechanism utilizes a logical concept known as reference counting. In other words, in the implementation of the shared pointer, in the representation of that particular instance, we maintain a value that indicates the amount of pointers that point to a particular location in memory. And anytime we copy construct a shared pointer from another shared pointer, that manipulates that reference count. And the point of the reference count mechanism is to achieve the desired goal that, and by the way, this is automatically handled by the implementation of the shared pointer, in particular in the destructor. We want to achieve the desired effect that we do not free any memory associated with a particular shared pointer until the last shared pointer associated or pointing to that particular location of memory goes out of scope. And so the shared pointer mechanism enables us to achieve that objective, and so consequently we will be utilizing it in our implementation of how we represent the information relating to the results of a query, the query operation. So we'll be discussing various different things relating to the shared pointer as time passes by. So in other words, we've discussed the abstractions. In other words, just to be very succinct once again, we have created an abstraction that the implementation of which automatically constructs the necessary pieces of information that enables us to query the contents of a file easily. That's the first abstraction. And the second abstraction is the one utilizing the return value of the query member function, which is a proposed member function of the initial abstraction we talked about. And that abstraction will contain various pieces of information relating to what we associate with the result of a particular query, what we want to associate with the result of a query. And so using these, what I call high-level abstractions, we can implement the program as follows. So I'm going to outline a high-level code fragment that utilizes these proposed abstractions, and then we'll proceed to actually implement these abstractions concretely so as to provide the services required by this high-level implementation. So suppose we have, and I'll talk through, by the way, in the last lesson I talked about the distinction between literally interpreting code programs and understanding their logical foundations. They're two distinct things, and the most important thing is understanding a program's logical foundations. And in relation to literally interpreting programs, I refer to that as analyzing its technical specifications. In other words, if I write something like void, if I specify a function prototype, like so, then in terms of literally interpreting this particular code fragment, I refer to that as understanding its technical specifications. In other words, this is the specification of a function returning no value as indicated by the void keyword called func with no parameters, and so on and so forth. So let's implement this high-level code fragment, and I will discuss the technical specifications and then actually go through its logical foundations in terms of what we are trying to achieve, logically speaking, after I've outlined the high-level implementation. So we have a specification of a function returning no value called run queries, with a single parameter, which is a reference to an object of type ifstream called n. And what we do is we create an object of type TextQuery, and this is the first abstraction we were discussing, called TQ, and we pass the parameter passed to the run queries function to its constructor. We will go over the totality of this code fragment in a second. We employ the use of the while construct, the target expression of which will always value to true, and so consequently there must be some mechanism for terminating repeated execution of this particular loop body, and there is, and we will discuss that in a moment. And I could be overly general here and say we are specifying an object of type cout as the left-hand operand of the output operator and so on, but I think that would be, in terms of, if you have a basic understanding of the C++ programming language, it'll be fairly simple to understand what this particular piece of the code is doing, and so consequently I won't be overly general in my analysis. I would just say the following. We are printing to the console window the following string. Enter word or Q to quit. And we can already see what conditions under which we will terminate the repeated execution of this particular loop body, as indicated by this particular string here. And what we do is we create an object of type string called s, and then we employ the use of the if construct, the target expression of which takes the inverse of the result of reading into the string s, and we use the logical OR operator, and we make use of the equality operator to check for s is equality with the value q. Now, in terms of, we will discuss these logical foundations in a moment in terms of what's going on. If this condition evaluates as true, then we will execute the following statement. One second, sometimes, a lot of times I sort of think of something and then I forget it. So I'm actually just going to write down what I need to discuss here. So on a piece of paper. That's fine. And let's see here. So that's fine. And if the target expression of the if condition of the if construct evaluates as false in terms of its totality, then we will execute the following function call. We call a function called print, passing the object cout, and the result of calling the query member function on the TQ instance, passing to its implementation string s. And then we will apply the manipulator NDL to the stream. And that's the end. So in terms of discussing what's going on here, again, this is using the high-level abstractions that we proposed previously. And so let's go through it in detail. This particular statement here declares an object of type TextQuery. A TextQuery is an abstraction that represents the contents of a file in a way that is easy to query. And as such, it provides a query operation which we use in the implementation of this high-level implementation. And so what we do is as follows. First and foremost, in terms of what this parameter represents the file. In terms of what the ifstream type is, and again we have to pass it by reference because we cannot copy an object of type ifstream, but ifstream represents a mechanism for interacting with files, reading from files, and it provides various different overloaded operators in order to achieve that objective. And so consequently what we do is we pass to the parameter a particular object of type ifstream, and that particular object, let's suppose, is bound to a file called text.txt. And what we do is we pass that parameter to the constructor of the TextQuery implementation, to the constructor of TextQuery, and that constructor is implemented in such a manner so as to construct the various different pieces of information, the representation that will enable us to query the contents of that file in a way that's easy. So that's what this abstraction is about. So the next thing that we do is we want to provide the mechanism to the client of our application of being able to repeatedly query the contents of the file. And so consequently we need some mechanism for repeated execution, and to do that we make use of this while construct here. And the while construct very simply evaluates its target expression, and if it evaluates it true, it executes its loop body, and then once that is done, it evaluates its target expression again, and if it still evaluates it true, then it will execute the loop body once again, and so on and so forth. Note that the target expression in this case is true, and so consequently it will always evaluate true. And so the implementation of the loop body must contain some terminating condition, which it does. And so here's what we're trying to do, logically speaking. We have constructed this text query instance that represents the contents of the file. And what we want to do is we want to provide the user the ability to query the contents of the file. So we prompt the user, enter a word or Q to quit. And so consequently what we do is we create an object of type string called s in order to hold that input. And here's what we do. Let's analyze the target of this if statement in detail, and then we'll discuss the purpose of the if statement in and of itself. So within the context of in the target expression of the if statement, first and foremost we employ the use of this binary operator, which is the logical OR operator. And okay, we'll discuss that in a moment. Here's what's going to happen. Actually we'll discuss this first. So the first point is this. The OR operator, the logical OR operator, provides what's called short-circuit evaluation. In other words, logically speaking, the OR operator is used in contexts where we want to say, if some condition is true or another condition is true, execute a certain body of statements. And so consequently, if the left-hand operand of this particular operator evaluates as true, then that implicitly determines the result of the overall expression, and so consequently there's no need to evaluate the right-hand operand. As a consequence of this, the logical OR operator guarantees the order of evaluation of its operands, and so consequently it's going to evaluate the left-hand operand in its totality. And the left-hand operand takes the inverse of applying this particular operator to these objects of types to the types of the objects S and Cn respectively. Now what's going to happen here is we need to, in order to evaluate this left-hand operand, the first thing we need to do is we need to evaluate what this expression means here. And to put it simply, it's going to enable the user to input a string on their keyboard and store it within the representation of the S instance, the string instance S. Now here's the key thing. We discussed this in the last lesson. The implementation of the overloaded bitwise left shift operator when applied to objects of type Cn will return its left-hand operand. And the implementation of Cn in and of itself must therefore supply a mechanism for implicitly converting itself to bool. And in terms of how it's actually implemented, it implements a conversion operator to bool such that it can be implicitly converted to bool, and the implementation of that operator presumably does various different checks on the representation of the Cn object, like for instance checking if it's hit end of file or any other kind of error, and then returns the appropriate true or false value. And so, to put it simply, to put it in friendly terms, what's going on here is we're saying the result of this particular operation here will be true whenever we implicitly convert it to bool, will be true when everything's gone well. And it will be false if something's gone wrong, like we've hit end of file. And so what we want to do is, if we want to specify that if it has encountered some kind of error, then we want to exit the loop body because we do not want to continue whenever the object's representation is in an error state. And so consequently what we do is we implicitly convert the object of type Cn to bool, and then we take the inverse of that such that whenever it's false it evaluates to true, meaning that we will execute this break statement and exit the loop body. Now if this evaluates as false, which is what we would like whenever, in terms of being able to provide the user the ability to query the contents of the file, then we will evaluate the right-hand operand of this expression, which uses the equality operator on the... One second, I have to double check. This is double quotes. Okay, let me just get the black pen. We use the equality operator to put it simply. What we're doing is we're checking, is the string that S represents equivalent to Q? Now to be more abstract in general, we're applying the equality operator to an expression, the context of which we're applying the equality operator to operands of type string and an operand of a built-in of a string literal, which is, in terms of what a string literal in terms of what its built-in representation is, it's an array of char, in particular an array of constant char. And the implementation of the string facility provides an overloaded operator that enables us to check for the equality of a string with an object of this built-in type, or in other words a string literal. So to put it simply, what we're trying to achieve here is if the user entered in their keyboard Q, then that means they want to quit, and so consequently we need to provide that service. Now if they did not, and everything has gone well, then what we want to do is we want to, and this is the print function here, first and foremost, this particular sub-expression returns the first parameter, in terms of the way I specify it, this is an argument to which the argument is supplied to the parameter, which is the interface of the function. But in terms of, strictly speaking, the implementation of print returns the first parameter, and so if it's a reference, it's in effect returning its first argument. And so what we're doing here, what this print function represents in terms of its logical foundations, is we're attempting to print the results of a particular query. And in order to obtain the results, we call the query member function on behalf of the TQ instance. And we do that here. And in order to call the function, we need to evaluate its arguments before we can actually invoke it. So consequently, we'll invoke the query member function on the TQ instance, passing to its interface s, and that will essentially provide the in terms of semantics, the service of querying the contents of the file for the occurrence of a particular word, and it will produce a query result that relates to the amount of times the word occurred, the lines that it appeared on, and so on and so forth. Just to be clear, the query operation is returning an object as a query result. We pass it to the implementation of print. The print implementation then prints out the various different pieces of information it needs to, and then we use this manipulator here to manipulate the state of the stream. And that's it. So that's all that's going on here. So in other words, what we're saying is this is a high-level piece of code that uses our proposed abstractions, and so consequently our next task is to implement the services provided that need to be provided in order to get this particular abstract code fragment to run. So, taking into consideration the use of these abstractions, let us implement the services they provide. We will implement them and discuss them at length according to the principles set forth in Lesson 1. So, one moment. Okay, so let's implement this text query abstraction using the abstraction mechanism as represented by the class mechanism. And so to do that, I'll talk through the technical specifications and then we'll discuss what the different components represent in terms of their logical foundations. So first and foremost, the implementation makes use of a class type called query result, which represents the result of a query. And so consequently, we need to forward declare this particular class type. Note that it's an incomplete type, and so consequently, we can only use it. Actually, I would need to check that. But the point is, we need to forward declare the query result class. That's the first point. Now let us implement this abstraction called TextQuery. We do that by means of the class mechanism. And so we're declaring a class type called TextQuery. And we specify public access specification, meaning that the implementation specified in this section is accessible to general users of the class. And the first thing we do is we employ a using declaration to associate the tokens that constitute this particular string, line underscore no, with the following type. And this is going to be a long type, so we'll slide over here. First and foremost, we're attempting to access the vector the vector facility, which is located in the standard namespace, and it's a template, and we're attempting to access the vector implementation when instantiated with type string, which is in and of itself located in the standard namespace. And we're trying to obtain the size type member located within the context of this particular instantiation. And we do that by means of the scope resolution operator here. Now the reason that, okay, we'll discuss this, we may as well discuss it as we're walking through it. The reason that we're using this declaration here is because we're going to need to use the type represented by this notation here quite often through our source code, and so consequently we don't want to write out this very verbose name every time we want to access that type, and so consequently to simplify matters we make use of this using declaration. So the next part of our implementation is the constructor, and we will implement that shortly, but we will specify its prototype, and as indicated by the high-level code fragment, its parameter is an object of type ifstream and it's as simple as that. Now the next thing we want to do is we want to, and this is the reason why we had to forward declare the query result class, because we're using it in the specification of the return value of the query member function, and so that's what we're specifying next. We're specifying the prototype for the query member function, and as indicated by the high-level code fragment, its parameter is an object of type string, in particular a constant reference, because in the implementation we do not wish to modify it. And we make this member function const, which essentially, one second, which essentially modifies the implicit this parameter such that it is a constant reference to the object upon which we initiated the query member function. So, in other words, a constant member function cannot be used to modify non-constant data members or call non-constant member functions, because a non-constant member function can implicitly modify a non-constant data member, and of course a constant data member can't be modified anyway. So the next thing we want to do is we want to specify private access specification, because we do not want general users of the class to be able to access the representation that we're going to specify. So the first point we're going to note, and we'll discuss how it works at length. We'll discuss what it represents at length. The first data member is a shared pointer, and I'm going to talk very abstractly here, and I will come back to discuss this throughout this lesson. A shared pointer that can point to an object of type vector whose elements are strings called file. Now here's the general point. The reason that we're using a shared pointer is because we need to synchronize in some manner the lifetime of the file that represents the vector that represents the contents of the file across different class types. One class type being the TextQuery instance, and another class type being the query result instance. And the implementation of the shared pointer will automatically handle in its destructor the process of freeing memory associated with the vector, essentially freeing the space associated with the vector that represents the contents of the file. Now, I was going to discuss this at some point. We will discuss some details of how shared pointer works later on in the lesson. But essentially what's going on here, first and foremost, the way I like to interpret statements like this is we have a shared pointer, which is essentially a pointer that share state with various different other pointers of the same type, we have a shared pointer to an object of type vector that can hold strings, called file. That's the way we interpret the statement. But to be general about this, what we're doing here, again, if we were just to replace the tokens that constitute these various different strings with arbitrarily complex strings, then there would be no way to reason about its logical foundations, and so consequently we would have to be general in our analysis. And so to that end, uh, what's going on here is we're declaring an object of type shared PTR, which is a template instantiated with vector, which is a template instantiated with string, which is actually a synonym for a template. And the result of that is called file. But in terms of its logical foundations, it's a shared pointer to a vector that holds the contents of the file. Now here's the next part of the representation. We have a map. And the map essentially maps objects of type string to objects of type shared pointer. And again, we already discussed we could say shared pointer instantiated with, but to be more relatable, I will say a shared pointer to, and this is the shared pointer. I haven't indicated the angle bracket token. A shared pointer to an object which is located in the standard namespace of type set instantiated with line number. And then we have various different tokens here just to end all those different template instantiations called WM. Now as you can see here, we're making use of this synonym line number. Essentially the set, in terms of, okay, let's discuss this first and foremost. We have a map that maps objects, and if you don't know how the map facility works, then I'm sure there are various different tutorials, very simple tutorials that will discuss the very basics of the mechanism. But essentially what it does is it maintains in terms of its representation, various different objects of a particular type to which it associates an object of another type. And so in this instance, we're maintaining various different objects of type string to which we are to associate shared pointers to sets instantiated with line number. And what we're trying to do here in terms of its logical foundations is we're trying to take every word in the input file and represent it as an element in this map and associate with that word. And this is about achieving the logical objective that we want, which is, and we specified this earlier, we're trying to associate with each word the set of line numbers on which that word appears within the context of the file we're working with. And so in order to achieve that objective, we need some mechanism that can record and store that information for us. And so the implementation of the constructor will do that, and this particular data member will act as the mechanism by which we can store that information. And so we associate with each string, which is essentially a word, a set. And that set's going to contain various different integral values. And of course, the reason we're using the line number synonym is because we need the integral type associated with the instantiation of vector indicated up here, instantiated with string. We need that integral type, and so consequently we could write out the full specification, but it's easier to use a using declaration. It makes the code more readable. And so what we're trying to achieve here is we want to associate with each word a set of line numbers that the word appears on. But here's the critical piece of information. We're not storing that set. In terms of the set abstraction, it may in and of itself cause dynamic memory allocation, but the representation directly within the context of the set abstraction will be stored on the stack. And so consequently, Uh, so anyways, the representation of, if we just declared an object of type set, uh, then that abstraction contains various different uh, data members, presumably. And in terms of the way that we store those data members might point to dynamic memory. But if that data member, for instance, contained a pointer, that's going to be stored on the stack. And so consequently, we don't have a mechanism for being able to share this information, which we need to, because the query result has to represent this information also with other instances. And so consequently, the reason that we're declaring this to be a shared pointer is because we want to give query result access to the sets associated with each word. And so that's what we're doing here. And that's the end of our implementation. Very simply. So let's just go over, let's go over some of the basics of it. Like so, we've already gone through it in relatively good detail, so there's no need to go through it again. Okay, that's fine. So here's what we want to do next. We've set out this skeletal structure that pertains to data members that are capable of representing and storing the information that we need to associate with a given input file. And so consequently, what we need to do is implement logic that can actually initialize, perhaps not in the technical sense initialize, but in practical terms initialize that representation. And so what we do in order to achieve that is we implement that logic within the context of the TextQuery constructor. And so that's what we'll do next. We'll implement the TextQuery constructor, and we'll talk through it at length. Now, we're implementing the TextQuery constructor outside of the body of the class specification, and so we need to gain access to the scope of the TextQuery constructor, and so we do that by means of the following notation using the scope resolution operator prefixed by TextQuery, and we're defining the TextQuery constructor. And of course, the parameter is a reference to an object of type fstream. The reference, did I mention that? We'll call it is. And in the constructor initializer list, I'll try to write this over here. In the constructor initializer list, what we do is we initialize file. 1 second, let me just refer back. Yeah, that's fine. So we have file. We initialize file to the result of the new operator, which dynamically allocates an object of type vector and instantiate it with string. And that's fine. In other words, this file is a shared pointer to a vector. In other words, file is a shared pointer that is capable of pointing to a dynamic vector, which is a dynamic sized array. And so to initialize that shared pointer, we dynamically allocate a vector of type string. Whenever you first learn C++, you basically just regard this as being synonymous with the statement a vector of type string or a vector that can store strings. But of course, to be overly general in our analysis, we could say vector instantiate with string, and that implies a whole series of different things. But we're initializing the shared pointer with the return of the new operator, which is going to return a vector dynamically allocated. So that's fine. And then what we need to do is we need to implement within the context of the constructor the logic that is necessary in order to initialize the representation such that it makes querying the file a relatively trivial task. That is what we're trying to do. We're trying to take the fundamental operation of querying the file, encapsulate the complexity within the context of the TextQuery class specification, and then provide a well-defined interface in order to perform useful operations such as querying the contents of a file for a particular occurrence of a word. So that's what we need to do. So let's talk through what we need to do here. So first and foremost, we declare an object of type string called text, and we'll talk through technical specifications before going through the logical foundations. Actually, no, we'll go through the logical foundations as we go through this. So we declare an object of type string called text, and the reason that we're utilizing this, we're declaring this particular object, is because we need some mechanisms to store the information that we're going to read from the file. So what we need to do is as follows. And by the way, this relates to the term algorithm. This is what I would consider to be an algorithm. A series of steps, a unit of computation, a series of steps executed in a sequential fashion in order to perform some specialized task, in order to provide the services required by higher level code. So we're essentially implementing an algorithm at this point. And so what we're doing here is we're essentially, as I said, we're trying to initialize a representation. It would be useful to see the wider context, but we're not going to be able to see that until we write it out. And so consequently, I could refrain from discussing the logical foundations until that is done, but I'm not going to do that. We have a string, we declare an object of type string, and that's going to hold the input from one line of input from the file with which we are working, which is passed to the interface of the constructor. So what we say is as follows: we employ the use of a while construct, the target of which is the result of calling getLine, passing to its interface an object of type cin and text. This particular statement here will provide the service. The getLine function will provide the service of. No, that's wrong. Yes. The getLine function will essentially provide the service of looking at the file that the parameter is bound to, which for the sake of argument, suppose is called text.txt, and read a line, the first line of that file, into the representation of text. And then the result of that getLine is implicitly convertible to bool, and then that essentially enables us to check if the operation performed by its implementation was successful. So in other words, we're saying read the first line of input from the file associated with the parameter into the text string instance, and if that was successful, perform the following actions. If not, then we encountered an error. Note the terminating condition for this particular while loop is whenever it hits end of file. In other words, when there's no more input to read. So let's implement the logic of this particular loop body. So here's what we want to do. First and foremost, refer back to the representation. The file data member represents each file in the input. It is a vector that represents every single line in the input file with which we're working. And so consequently, we want to add that string to that particular vector, and we can do that with the following notation. This is the arrow operator here, and we will discuss what that means in a moment. So essentially what we're doing in this statement is we are obtaining the vector to which the file pointer refers, and calling the pushback member function on that instance and supplying to the interface text. So that will provide the logical service of adding to the vector to which the file shared pointer points the string text, which enables us that provides the mechanism for recording and storing every single line in the input. Now in terms of the arrow operator, what's going on here? Well, suppose for a moment that file was a built-in pointer. The arrow operator is essentially shorthand notation for parenthesizing file and dereferencing it within the context of that parenthesization, and then applying the member selection operator in order to fetch a particular member of the instance to which the pointer points. So so essentially we're dereferencing the thing to which the file pointer points, and then uh, and then applying a particular the member selection operator to fetch a particular member of that class instance. Now in this case, file is a shared pointer, and so consequently the arrow operator must be overloaded. And there are certain things, I can't quite remember the details, and this is one thing I would say. A lot of times you study, you read a lot of books and so on, and you learn the fundamental first and foremost, you have to prove that you're able to understand everything. And secondly, you have to remember the overall larger concepts involved. You don't have to remember every single detail. That's not important until you begin implementing a solution that makes use of a particular facility, in which case every single detail is going to have a huge impact on the behavior of the code, and so consequently must be taken into consideration. But having said, so taking that into consideration, I don't remember the precise constraints on the overloading of the arrow operator, but it has to, for instance, return a pointer as its left-hand operand, for instance, and so on. To which we apply the operator. I think that's the case, but I would have to look back at that. Anyways, look, here's what we do. So here's what we want to do. The next statement is about, we declare an integer called n, and we initialize it to the return of calling the size member function on the vector to which the file pointer points, -1. In other words, we're trying to remember we are trying to record the current line number. Now here's the next thing that we do. So we have added the string to the vector. We have recorded the line number associated with that particular string, and that's going to come into use momentarily. And the next thing that we need to do is we need to initialize the representation suitably, in the sense that we need to take that input string and we need to break it up into the individual words it's composed of, and then record those words in some meaningful way. And so to do that, we make use of the iStringStream library facility. And so we declare an object of type iStringStream. One moment. Called line, and we bind it to text. And this mechanism is essentially a mechanism for performing in-memory I/O. In-memory I/O, that's what it does. And so you'll see what it enables us to do in terms of the facilities and the features that it provides in a moment. So in other words, this mechanism is about it's going to help us take that input string and compartmentalize it into the various different words that it is composed of. So here's what we do next. We declare an object of type string called word. And this is essentially going to represent an individual word on that line of text. And here's what we do. We employ the use of a while construct, and the target expression reads the first word in the string to which the line iStringStream instance is associated into the string representation for word. So in other words, the logical service provided by this particular statement, first and foremost, we're making use of a while loop, and the reason for that is that we essentially want to repeatedly read the various different words located in the input string associated with the iStringStream instance into the string instance, and then we want to perform some additional logic that's necessary in order to provide the semantics of initialization of the representation and so on. And we want to do that until there are no words left within the context of that input string. And that while loop will take care of that for us, because this will essentially repeatedly execute until this hits end of file essentially. So the logical service is it takes the input string associated with the iString stream, applies this operator, the implementation of which when applied to iString streams will read every character up until the first space, I believe, into the right hand operand, which is a string instance in this case. Now what does the implementation of this body do? So the first thing that we do is we make use of the auto type deduction mechanism to declare an object called lines initialized from subscripting the representation relating to the map data member with an index word. Now here's the important thing to understand here. If what we are doing, we need some mechanism to add words to and we're going to discuss the complexities of logic in a moment, but we need some mechanism to add words to the map representation, and the mechanism for doing that is to use the index operator, because the index operator is defined in such a manner so as to automatically add a particular class instance if it's not located in the map whatsoever. And so consequently, the first time we execute this statement, it's going to add the string word, the object represented by the string instance word to the map. And then the result of the index operator is the type, is an object of the type to which the map maps its first type. In other words, a vector of sets. So in other words, what we're doing here is we're returning a vector of sets, and then we obtain a reference to it, and we use the auto type deduction mechanism to prevent verbose notation. So we obtain a reference to it, and the reason we obtain a reference to it is because we want to modify that value returned. And we'll discuss that in a moment. Oh no, that's incorrect. It's a shared pointer. Excuse me, it's a shared pointer to a set of line numbers. Did I say that? I'm not sure. Anyways, the point is the distinction is immaterial because the logic is the same. We need to manipulate the value to which a particular string object maps to in the context of the map. And so consequently we need to obtain a reference to it. We use the auto type deduction mechanism to avoid verbose notation. And so here's what we do. Here's what's critical. We employ the use of an if construct, and we check the target expression of which is taking the inverse of lines. Lines is a shared pointer. When the inverse operator is we'll discuss that in a moment. Okay, when the inverse operator is applied to a shared pointer, it essentially checks if the pointer is null or if it has already been initialized or assigned. In other words, does this pointer point to something or does it not? And the inverse operator, when applied to an object of type shared pointer, enables us to fulfill that logical role. And so essentially what we're asking is the shared pointer valid? And that corresponds to the built-in semantics whenever we apply the inverse operator to a built-in pointer. And if it is not, then what we want to do is we want to execute the following statement. We want to call the reset member function on the lines instance, which is a reference, remember, to a shared pointer. And we want to pass to it the result of calling the new operator, which dynamically allocates an object of type set, whose element type is line number, which is something that we have previously defined. So essentially what we're doing here is we're saying if when we add a word to the map, if the value associated with that particular word, which is a shared pointer, is not initialized, then initialize it by means of the reset member function, which will essentially assign to the shared pointer the result of the new operator, which dynamically allocates a set of line numbers. And in so doing, we have essentially dynamically allocated a set to be associated with that particular... Oh crap. I don't know why it's doing that. Okay, I'm gonna try to rub that out. Actually, no, I can undo that. Okay, anyways, look. So that's fine. So that provides the mechanism for initializing the value to which the string object maps to. And then what we do is we say lines or operator insert n. And then we will end the implementation of the constructor. In terms of what's going on here, if you analyze the logic in detail, let's analyze this statement before we move on. We're of course applying the OR operator to the shared pointer in order to call the insert member function on the pointer on the object to which the pointer refers, passing to the interface n. In other words, we're providing the logical service of adding to the set associated with a particular the set represented by the reference lines, the value n, and the value we recorded the value n previously up here. In other words, the logical service this constructor is providing in this particular segment uh, is it's taking, by the way, you have to understand, if we have to, okay, we'll discuss that in a moment. It's taking each word in the input file, adding it to a map, and recording every single line number that it appears on. And the important thing to understand here is that whenever we index a map with an object that already exists in terms of equivalence within the representation of the map, it will retrieve the shared pointer associated with that particular object. And so consequently, a consequence of this is that we won't execute this particular statement, and we will then insert the line associated with that word, which is the line in the current iteration of the while loop that we are working with respect to the input file. I'm not quite sure what I just said, but anyways, so that's fine. So again, just to reiterate, what's important to understand in terms of what's going on here logically is we have a map, we're indexing it with a particular word. If that word already exists, then this particular statement will not be executed, and we will just add the line number associated with the current iteration to the set associated with the shared pointer associated with that particular instance. And the important thing to understand here is that whenever we go back up to the top of this, by the way, you have to understand another thing. I nearly forgot it. That relates to the point I made at the start, which is that I might forget some things. You have to understand the implementation of set. The normal set library facility only permits a single instance of a particular value to be located within its representation. It does not permit multiple instances with the same value, and furthermore, it implicitly uses the less than operator in order to order its elements. And so consequently, if we read two words on the same line, we're not going to, the insert member function is going to have no effect. So that's the first point. And the second point is, whenever we go up and we iterate again with respect to this particular while loop, we're going to update the value of n. And if we encounter the same word again, then we're just ultimately going to insert that line number into the set associated with that particular word, which is represented by the map data member. Okay, that's fine. So that's the logic of the constructor. One second. So that's the logic associated with the constructor. Okay, so the next thing we would like to do is we would like to specify query result. We forward declared it before, but now we want to implement it. And so we will do that using the class mechanism. So we're declaring a class type called query result. And the first thing that we do is we specify that a particular function is a friend. In other words, we want to provide access to the implementation of the query result class uh, to this particular function. And this particular function returns a reference to an O stream. The function is called print. Again, this function prototype. It's not a prototype in the sense that we have to declare it elsewhere. I don't believe friend declarations, although I may be wrong, friend declarations count as a declaration of a function, so it has to be declared somewhere else. But this, we'll call it a prototype for the sake of argument. This prototype essentially relates to the high-level abstractions that we used in our high-level code fragment in order to provide the service of printing the representation of a query result. And so suitably, it will have a parameter which is a reference to an object of type OString, and a constant reference to be precise, to an object of type query result, because we wish not to modify the query result instance. So the next thing that we do is we specify public access specification, giving general users of the class access to this particular segment of the implementation. And we specify a constructor, the implementation of which will be defined within the context of the class definition itself. So it's a constructor, and so consequently has the same name as the class type itself, with a parameter of type string, a parameter of type shared PTR, which can point to an object of type set, which stores line numbers, which is an integral type, associated with a particular vector instantiation. And we'll call this parameter P, and then we will specify the last parameter, which is also a shared pointer to a vector that can store objects of type string. And we will call this parameter F. And essentially what these parameters represent, the string parameter represents the word associated with a particular query. The second parameter is essentially a shared pointer that points to the set that contains the line numbers on which that word appears, which may be empty, by the way. And presumably the implementation, in fact, let me just check this. Yes, the implementation performs the necessary checks in order to print the appropriate information if it is empty or if it isn't empty. And the last parameter is essentially a shared pointer to the file contents, so that we can easily print it out. Again, the reason we opted for shared pointers was because we didn't want to have to copy the vector, because that might be a very expensive operation, because the file might be quite large. We use shared pointers, and that way, not only do we give multiple different class types and class instances of different types access to that shared state, but the shared pointer mechanism ensures that that memory isn't freed until the last shared pointer associated with it goes out of scope. And we will actually discuss some nuance related to shared pointers within this lesson. Now, we have a constructor initialized list, and what we do, and there's 3 different data members. We initialize sort, which in terms of the name choice, indicates that that's the value we were looking for. We initialize sort with S, lines, which is another data member, with P, and file with F. And the function body has nothing to do. Now we'll specify the representation over here because we don't have enough space. We have private access specification, meaning we do not permit general users of the class to access this part of the implementation. And we have a data member of type string called sort, as indicated before. And that's the word the query represents. We have an object of type shared PTR that can point to sets storing integral values called lines. And last, we have another shared pointer which can point to a vector, which is dynamic. We will discuss vector implementations in upcoming lessons. And the vector can store objects of type string called file. And that's our query result implementation done. So there are only 2 more fundamental pieces of information that need to be implemented in order to get this abstract specification, which we wrote earlier in the lesson, to function. We need to specify the query member function and also the print mechanism. And so we will do that next. We will specify the query operation. Okay, 1 second. Okay, so let's implement the query operation. So the query operation, as specified before, returns a query result. And the reason for that is because we need to return multiple pieces of information, so we can specify that within the representation of a class type, so as to enable the return of multiple pieces of information. And we need to access the context of the TextQuery class, so we use this notation here. The member function is called query, and as indicated before, it has a parameter, which is a constant reference to an object of type string called sort. And it's also a constant member function, the basic implications of which was already discussed. So, what does the implementation do? So, the first thing that we do, and we will justify this shortly, is we declare a local static variable of type shared PTR, which can point to sets storing integral values, and we call this no data, and we'll explain that relates to its purpose. And we assign it the result of the new operator, which dynamically allocates a set of line numbers. Note that it's dynamically allocating an empty set. Now, in terms of what this shared pointer represents? It represents the value that we are going to return if the word that we're looking for, in other words, if we supply a word, uh, if we supply a particular string to the query implementation, such that that word does not exist within the map representation, then we need some way to indicate that the word wasn't found, and so consequently we define this local static shared pointer variable in order to indicate the default case whereby the word wasn't found, and so consequently we called it no data. So here's the crucial thing. The next thing that we do is we declare an object using the auto type deduction mechanism called loc, and we initialize it with a result of calling the find member function on the map data member, passing sought. And the logical service this is providing, so essentially what we can't do is we can't index the map, because as we have learned previously, indexing will automatically add an entry corresponding to the object we passed. And so consequently, it would always seem to be the case that the word that we're looking for was supposedly in the map to begin with, but of course that isn't the case. So we can't use the index operation, we have to use the find member function. And the find member function is essentially going to look in the map for a particular occurrence of a word, and it's going to return an iterator to it. Now I can't remember the specific details. If in terms of the map representation it utilizes pairs, and the find member function returns an iterator denoting a pair associated with that particular word. I can't remember the precise details, but that's immaterial. The point is, in the abstract sense, we obtain an iterator denoting the element associated with the particular word that we're looking for. And here's what we do. It's very simple. We say if what the find implementation will return if it doesn't find the element that we specify is the end iterator. In other words, the iterator that denotes the one past the last element in the sequence. And so what we do is as follows. We essentially test if loc is equal to wm.end. We call the end member function essentially to obtain an iterator to one past the last element. We don't even need this. And if that's the case, then we return a query result passing to its constructor sought, no data, and we'll make use of that parameter in the implementation of print and file. So this essentially represents a query that was not successful in the sense that it didn't find a match in terms of the value we were looking for. Otherwise, we want to return a query result constructed with sought, loc our operator second. Okay, now I know. So loc is an iterator to a pair. So now we know. See, but these details are immaterial in my view. You know, just remembering the general concepts is what's important, and being able to understand something is what's important. But essentially, what we're doing here in the abstract sense is that we're constructing a query result with sought, the result of applying the OR operator to loc, and fetching the underlying member called second, and file. Now, file represents the contents of the file that we were working with, and so on, and that's stored in the representation of TextQuery. And so we pass that on to the query result instance. We're passing sort because that's the word we were looking for. And as I say, what we're doing here is we're essentially dereferencing this iterator and obtaining the second member associated with it. This iterator refers to a pair. We dereference that to obtain the pair, and then we apply the member selection to obtain the second data member, which will essentially denote the set of line numbers associated with a particular word, which is this word here. And that's what we do. And that's the end of our implementation. So this query operation essentially provides the service of inspecting the contents of the file to see if a word appeared, how many times it appeared, and so on. And that information is neatly represented by various different data members and so on, which we access in the implementation of the query member function. Okay, the last piece of the puzzle that we need to implement is the print member function. No, it's not a member function, it's a friend function. And so we will proceed to specify that now. In accordance with the prototype specified previously, we return an object, a reference to an object of type OStream. The function is called print, and it has a parameter which is a reference to an object of type OStream called OS, and a reference to a query, a constant reference to a query result called QR. Now we don't wish to modify the query instance that we pass, and so consequently it's a constant reference. And furthermore, the print function is specified to be a friend of query result because it needs access to the representation, which is private. And the only way to achieve that is by means of the friend mechanism. So what does this do? So what we do is as follows. Again, essentially what we're doing is we're passing a stream, an output stream to which we can write. And conventionally that's going to be an object of type cout. It's going to be cout. And so what we're doing in essence is we're printing to the output the word that we were looking for, and then we print that it occurs and then here's where we make use of a particular member function. So what we do is we fetch the lines data member of the QR query, the QR object, and that represents the set of line numbers associated with the word. And we want to get the size of that set. And the reason that we're doing that is because the size of the set will implicitly detail. One second, I think somebody knocked at my door. I'm going to have to go down. Okay, I'm back. So essentially what we're doing here is we're obtaining the size of the set associated with the word in order to determine how many times the word occurred, because of course the size of the set will be the amount of times the word occurred. Note that this particular flavor of implementation does not take into consideration multiple occurrences of the same word on the same line. So in other words, it's essentially printing, technically speaking, not how many times the word appears, but rather the amount of lines it appears on, and it prints those lines suitably. And the next thing that we do is we make use of a function which we will suitably define in a moment, called make plural, and we pass that information to the implementation, and we pass a string literal, and we pass another string literal, and then we apply the manipulator to the string. In terms of the logical service this make plural function is providing, essentially what we're doing is we're printing out the word, and then we're printing it occurs. So for instance, suppose the word was cheese. We're printing cheese occurs, and then what we're doing is we're printing the amount of times it occurs. And if it occurred one time, then we don't want to print 1 times, ending with an S. We want to print 1 time. Now note, I have to look over the implementation of this particular function because it would seem to me that in order to be fully accurate, it would have to account for the case whereby the size is 0, because you don't say, actually, do you say 0 times? I think so. Okay, never mind. And as the point is, we're printing out the amount of times it occurs, and then, so we're trying to print, for instance, make cheese occurs, for instance, 1, and then we need to decide how to print time. Do we print TIMES or TIME? And the make plural function provides that logical service. And we'll implement that suitably very shortly. Get the rubber. Okay, what's the next service? So the next thing we need to do is we need to print all the different lines that the word appeared on. And so what we do to achieve that is we use a range for. And the range for uses the auto type deduction mechanism in order to automatically declare num with the type to which the type of the value returned by this particular expression here. We obtain the lines data member and dereference it. In other words, lines is 1 second. So lines is a shared pointer to a set of integral values. So we dereference that to obtain the set. We obtain the shared pointer and then we dereference it to obtain the set. And so what we're doing is we're essentially the range for construct is implemented in terms of calls to the begin and end member functions of the expression supplied as this particular operand. We can refer to it as an operand of this symbol here. That's how it's implemented, and so consequently we're essentially obtaining an iterator referring to the first element of the set that the share pointer lines refers to. And so num will be an iterator to that particular element. No, that's wrong, that's wrong. It won't be an iterator, it will be, it is implemented in terms of calls to the begin member function and so on, but num will just be an integral type, an integral value. And so what we want to do is we essentially want to iterate through all the different lines, numbers associated with a particular word, and we want to print them. And to do that, we essentially do the following. We print to the output stream. We use this particular uh, notation in order to provide desirable spacing. And we print line. So in other words, we want to provide a nice notation for our client, and we want to print the line number, and that's going to be num plus 1. And the reason that we do that is because in terms of how we represent the values of the line numbers, that there's a distinction here. And in terms of how we represent the line numbers, the values of the line numbers associated with different words, we use zero-based indexing because that makes it convenient to directly index the vectors that contain the input file. But with respect to a client user who is not a programmer, they're not accustomed to the convention that we begin counting at 0, and so consequently we need to suitably adjust the num value, and we do that by adding 1. And then we print to the output stream, and again, we've already discussed how we can chain together calls to the output operator. And then here's what we print next. We obtain the file data member of the query result instance. We call the begin member function on the object to which the share pointer refers. That will give us an iterator. We add num to get the nth element, and then we dereference that to obtain that element. In other words, this provides the logical service of printing the line of text associated with a particular word in this particular iteration. And then we outprint the end manipulator. And then what we do is we return OS in order to enable this particular, where is it? This general high-level code up here. And that's it. We're done. That's all there is to it. As you can see, this tutorial is much longer, and so consequently, you would be, you wouldn't expect. It's obviously not going to end here. There's much more to this. It's going to get a little bit more complex. But before it gets more complex, I must admit. Okay, let's discuss the logical foundations of this particular statement here, because I think that might give some people a little bit of trouble. It's a relatively simple statement. Essentially, the file shared pointer points to a vector, the contents of which represents the input file we are working with. And we want to obtain the line corresponding to the integral value in the set that we're iterating through. And so to do that, we call the begin member function on the vector to which the file pointer points and add num. And arithmetic on iterators is such that when you add an integer to an iterator, you obtain an iterator that many elements along. And so consequently, we obtain an iterator to the nth element in the general and abstract sense, and then we dereference that to obtain the element to which it refers, which in this case represents a particular line of text in the input file, and we print that to the console window. And in that way, we can print to the user not only the word that we were looking for, not only the amount of times it occurred, but also the full context within that which that word appears. Now, to be honest, this lesson will be much longer, as you can already observe by means of the fact that the tutorial is significantly longer. But I must go drink some tea because I'm quite dehydrated, and that's probably dangerous. Well, not very dehydrated, but I'm always very cautious of these things, so I'm quite dehydrated, so I'm going to have to go drink some tea, which makes it difficult for me to upload this. In fact, let me think about this. What am I going to do? Okay, I'm going to go drink some tea, because I'm going to need to do that. And then we will continue the lesson as soon as I get back. So give me 30 minutes. Okay, I'll see you in 2 seconds, obviously. Okay, so I'm back. I had to go drink some tea for an hour and a half just to make sure I was sufficiently hydrated, and now I'm ready to continue discussing uh, further details in terms of uh, example programs. And so just to reiterate in terms of where we left off, we just finished implementing the various different logical components required by our high-level function, run queries. That high-level function operated on the basis of various different proposed abstractions. We had to implement those abstractions and the services they ostensibly provided in order to get desirable program behavior, and we essentially ended up with an entire program that enables us to query the contents of a file for a specific word and obtain various different pieces of information relating to that query. Now, here's the important point. We are going to extend our implementation to make it slightly more complex and support more slightly complicated operations. And in that implementation, we are going to retain the various abstractions we initially implemented in our first program. In other words, the TextQuery implementation, we are going to retain that. It is an abstraction that provides the logical service of making it easy to query the contents of a particular file. We're going to retain that abstraction, and it automates certain processes such as building lookup files and lookup maps and so on. And we're also going to retain the query result implementation, but we're going to propose further additions to its implementation as required by the extension we are going to begin formulating momentarily. So let's get a new paint document here because we would like to run through another example. So let's begin. Now, we have looked at the implementation of a simple computer program that enables us to query the contents of a file for occurrences of a particular word. Let us consider extending the implementation to support more complicated queries. For example, and I'll write these out. The first operation, search for a word. The second operation is what we call a not query. And its associated symbol is this operator here, this token. It's the token used to specify the prototype for the destructor to enable distinction between the destructor and the constructor. The third is OR queries. And we'll discuss what the semantics of these different kinds of queries are in a moment. And the associated operator, we're just parenthesizing it just to emphasize its distinction from the main set of tokens here. We're talking about this specific operator here. That's the associated operator for OR queries. AND queries, and its associated symbol is what I believe is called the ampersand. It's the operator to declare references and take the address of variables. And finally, combinations of these kinds of queries. Now, in terms of, before I consider one final point in relation to this matter, what I will do is run through the semantics of the various different queries. So here's the general idea. The not query, which is this query represented by this particular operator here, it's a query that enables us to specify a particular word. So in other words, what we're doing here is we're starting off with specifying what the program should be able to do. In other words, what kinds of operations does it provide the client user of the application. And so the first point is that we want to be able to give the user the ability to perform what we call not queries. And a not query is very simply a query that returns every single line that a particular word is not on. So that's the first point. OR queries, and we'll talk about how we actually represent these different kinds of queries in a moment. We're just specifying the general design notions of the program at this current moment. OR queries, an OR query is essentially a query with two operands, a left-hand operand and a right-hand operand, and we will reflect that property in the implementation of the OR query itself, and also with the AND query. And the OR query returns the union of two word queries. In other words, what we do is we return every single line on which the two operands relating to the different words, every single line that they occur on. That's the idea of the OR query. So in other words, if I said we're not necessarily going to use this notation, but suppose I had a string literal 1 and I said OR 2, then the OR query mechanism enables us to return every single line that either 1 or 2 occurs on. And so therefore it returns the union in terms of its result. AND queries is the intersection. In other words, this query here. AND queries is the intersection. In other words, return every single line within the context of which both words are located. So in other words, if we had a particular line that one of the words was located on but not the other, we don't include that in our result. We're returning the intersection. And also we want to support combinations of these various different kinds of queries. So for instance, we want to be able to say something like, and we're not, this is just very abstract at the moment, we're just specifying the kind of behavior we wish to obtain, and that has to be made concrete by specific implementation and so on. But suppose we could use the following notation to support more complex queries. And we're going to discuss specific details relating to the notation to actually construct queries relatively soon. But this is the general idea. We want to be able to combine these different kinds of queries into a single expression and get the appropriate result. And this really relates to the last point I would like to make, which I was going to discuss before, but I'll discuss now. We're going to evaluate these kinds of expressions according to normal C++ precedent rules. In other words, specific operators have higher precedence than other operators, and some operators have equal precedence. And so consequently, in that context where the precedence is equal, we'll just evaluate it left to right. And so consequently, we would evaluate this expression first, and the result of it would form the left-hand operand of this operator here. So let's discuss some concrete notation in terms of let's discuss the kind of notation we want our implementation to allow. So, in other words, we wish to construct the appropriate implementation that enables us to compute expressions such as the following. In other words, we want to be able to say something like the following. And this is concrete now. We're talking about specific C++ code. This is the kind of notation that we would like to end up with. We want to be able to declare a class of type query called Q and initialize it from the following expression. I'm going to have to extend this just a little bit. Oh dear. Let me undo that. So just to reiterate, we're forming. This is the notation we would like our implementation to allow. This is in other words, we have ideals in mind in terms of the notation, and I suppose that the complexity arises in actually developing or formulating the code that enables this notation. And I'm using very bland names here, just to be very general. So taking into consideration this particular declaration, we will proceed to implement the appropriate code and discuss the implementation in its entirety once complete. So before we begin, I would like to discuss something of importance. Typically, whenever you're designing a program, you start off by first and foremost identifying what the program should be able to do. In other words, what is the main purpose? What is the functionality the program will provide? And then what you do is you carefully consider the design of the program in its entirety so as to understand how to begin to implement the program. And then you begin to implement the various different components using various different language and library facilities and so on. But that's not the approach we're going to take in this lesson. The approach we're going to take is we're going to implement the solution without justification and then return to how we actually derived that solution at the end of this particular section of the lesson. Again, just to reiterate, we're looking to extend our query system to support more complex queries, and the design task at hand here is developing the appropriate code that enables us to do just that. So I suppose what we're going to do is we're going to implement without justification. We're then going to put all the pieces together. In fact, what we're going to do is we're going to walk through the evaluation of a particular, what I would call, complex query, and then we're going to return to justify the implementation. Now, just to preface the following point, I would like to begin by saying that what we're going to do is we're going to develop various different components. And those components will work in such a way so as to provide the behavior that enables the notation that we just previously considered. So we're going to develop those components. And in terms of our implementation, our implementation is going to utilize the notion of the employment of various different abstractions. So in other words, we're going to represent the different kinds of queries as various different kinds of abstractions. And those abstractions encapsulate the logic necessary to perform the various different kinds of queries. And I suppose this is to be said without justification, but one thing that's going to be critical, and this will be easy to see in hindsight, is the fact that we have to employ a uniform interface. In order to get our implementation to work, because we're essentially going to manipulate. Our solution is going to utilize inheritance, and it will be a demonstration of how inheritance works. And in order to manipulate the various different kinds of derived classes, we're going to do it through a common base class, which provides a common interface. And so consequently, the various different derived classes have to provide a uniform interface. Now here's the key. Note that the notation used is not going to. Our intention is to develop all the necessary components in order to enable this notation here, and this extends over to here. This implies that the user of this particular language, the user of this particular library will not work with these proposed abstractions directly. They will instead indirectly create instances of the abstractions by means of this notation, this kind of notation here. And so what we're saying here is that in our solution, we're going to devise a relatively complex inheritance hierarchy, but then we're going to encapsulate and hide that complexity behind an interface class. And that interface class in this case will be the query class. So that's the general idea. And this, I suppose, relates to what I said in my first lesson, which is that if you're having, I'm not saying I have difficulty, it's a relatively simple program, but just in general, if you, the viewer, are having difficulty in understanding the logical foundations of a program, then one of the most useful techniques in order to get to that point is to take all the various different components that constitute the program and consider the employment of some notation or its various different kinds of inputs, and compute what the consequences of those inputs are in order to begin to understand the logical foundations. And so consequently, the approach I'm going to take is I'm going to discuss various different topics along the way. I'm going to discuss its logical foundations insofar as is possible, but ultimately the most revealing part of this particular section of the lesson will be when we consider the concrete evaluation of a particular notation, namely this notation here. So in other words, we're going to basically try to get this done as fast as possible. It may take an hour, it may take an hour and a half. Let's try to get this implemented as fast as possible. We'll try to discuss it as best as we can. And at the end, we'll consider a concrete example, and that will give you an idea as to how it works. So, let me just So I suppose there are various different points to take into consideration at this stage, and I suppose they seem unjustified because, quite frankly, it is necessary in some cases to actually have access to the implementation in order to see the connection between these points and the implementation. But I suppose a few points to note before we begin, and the first point is this. The idea is to formulate a uniform interface that enables appropriate execution of various implementations. That's point number one. Point number two, encapsulate complexity. Point number three, define an interface class to provide notational convenience for employment of this complexity. So that's the general idea. So let us begin actually implementing this. So once again, just to reiterate for the third time, we are extending our query system to support more complex kinds of queries. So here's what we need to do. And we're implementing this without justification. But I suppose in some sense that is beneficial because it will serve as an illustration of the power of taking various different pieces of code and considering their inputs in order to compute the consequences of those inputs. So we'll proceed as follows. The first thing we're going to do, and again this will seem like it's without justification, but we will return to justify it, is we're going to define an abstract base, what is essentially going to be an abstract base class. And so let us proceed to do that right now. We're going to define a class called query underscore base. And as the name suggests, it's going to act as the base class for various different derived abstractions. And the first thing we need to do is we need to make another class a friend. And the reason for that will be discussed shortly. So what we're saying here is we have a class called query base, and the first thing we do is we make query a friend. And the reason for that is because the various different members of query will call the virtuals in query base. So in other words, we're going to specify the virtuals. In this instance, we're going to define the different virtual functions as pure virtual functions. And then we're going to actually define specific implementations for those in the derived class. But we're going to manipulate those derived classes through the abstract base class interface. And the point at hand here is that this class is not supposed to be, it's an implementation detail. It's not supposed to be directly created by, in fact it can't be, we can't instantiate a specific version of this because of the pure virtual functions, and thus it is therefore an abstract base class. But I suppose the point at hand here is that we're going to specify these pure virtual functions, which we'll come to discuss shortly, as having private access specification, meaning that those facilities are not available to the general users of the class. And so consequently, if query is to call these virtual functions, it's going to have to be a friend of query base in order to access those private members. So here's what we do. We have protected access specification. Okay, so we have protected access specification, and the first thing we do is we have a using declaration to associate the tokens formed by this particular string with the line number within the context of TextQuery. And I believe that was public. So in other words, we'll call it line number for the sake of simplicity, is going to essentially represent an integral type. Now the next thing we do is we specify, and we'll come to justify why this is the case in a moment, the destructor as being virtual. And because we need to specify the function, the destructor to be virtual, we have to explicitly specify it, and so consequently the compiler will not automatically synthesize one for us. And so to request default semantics, we just use the following notation. And that way the compiler will provide a default meaning for the destructor. Okay. Let me get the rubber. Okay, the next thing we do, and we'll return to discuss why this is virtual in a moment. We have private access specification. And here's where we define the common interface. These are pure virtual functions. We define a function that returns a query result, and we will extend the implementation of query result suitably in due course, as they say, called eval, and it has a single parameter which is a constant reference to a text query. And remember, text query is the abstraction that essentially represents the mapping of different words to different line numbers and so on. And there's a constant reference, and it's a constant member function, and we specify it as being a pure virtual. So in other words, it is an abstract base class as a consequence of the introduction of this pure virtual function, thus meaning it essentially acts as an interface class, and we cannot instantiate a specific instance of this class. We have another virtual function which returns a string called rep. And again, the logical foundations in terms of what these functions represent will be discussed shortly, and it's a pure virtual function also. And that's the end of the implementation. So, in our solution, we will employ the use of a class hierarchy to represent various kinds of queries. Consequently, it becomes desirable to, if possible, place commonality in base classes and specialize the appropriate members to provide the desired behavior for a particular type. And furthermore, what needs to be discussed is that we're going to be manipulating the various kinds of entities through a common interface. And so that's why we're specifying these different functions to be virtual. Because it essentially is supposed to act as, and we're going to specify the precise mechanics of how that works in a moment. In fact, we will do that now. So the 3 points that I would like to note before we continue. Okay, I suppose what I will discuss is the following. So I suppose the first point to note is, in fact, I think it's a bit too early to discuss the meaning of the eval function. But at this point, what's important to understand is that we have two virtual functions, which are pure virtual functions, and we're going to derive various different class types from this particular class type and specialize the behavior that we want for that particular class type. So the first point I would like to note is that it's an abstract base class. There are, as a consequence of the fact there are pure virtual functions, and this particular class has no public members. It's intended to be used through an interface class. because it is essentially an implementation detail. Now let's discuss the following concepts that are of importance at this stage. So, the first point I would like to discuss is this: what is inheritance? Inheritance is basically a mechanism whereby you can take a pre-existing class implementation and inherit it into another class implementation, which may in and of itself have a particular representation, such that you essentially end up with two sub-objects that conspire to form a larger object. And so the general idea is, for instance, this is another notation we use, but suppose we have a class X, and we use the arrow operator to indicate that it derives from Y. Y might have a particular, let's suppose Y has a particular representation, like an int called X and a double called Y. Now there are complexities and nuances here in the sense that it all depends on the access specification that these particular data members are defined within, and also the kind of inheritance, whether it's public, protected, or private, and so on. All that determines whether or not these particular data members are visible within the implementation of the X class. But to be general and to be simplistic about it, we suppose that Y is a class that defines a particular representation denoted by these two variables here, and X derives from it. And X, furthermore, suppose X also defines a single data member, we'll call it Z. In this case, what we essentially have is a situation whereby if we create an object of type X called X, what's going to happen conceptually, and I suppose to an extent in terms of how it's actually laid out in memory, is it's going to create an object that consists of two sub-objects, one corresponding to the Y sub-object and one corresponding to the X sub-object. And the one corresponding to the Y sub-object will contain this particular representation here, and the one corresponding to the X sub-object will correspond to this representation here. So that's the general idea. It's a very simplified overview of what inheritance is, but that's a general idea. So why we're discussing this? Let's stay up here. There's a first point. The first point is this. Suppose I declare a pointer to an object of type X called 1, and I were to initialize it with a value with the address of X, which we declared right here. In that case, we would essentially have a pointer called 1 that can point to an object of type X pointing to the address of X, and consequently we could proceed to manipulate the underlying object by means of the following notation. In other words, we could dereference it and obtain a particular data member, like so, and then we could perhaps perform some modification of it if the access specification enables that. But here's what's interesting. As a logical consequence of the mechanism by which inheritance works, in other words, we have various different sub-objects that conspire to compose a larger object. What we can actually do is we can declare a pointer to type Y called 2 and bind it to the address of X. Now how does this work? Well, you have to refer to this particular diagram here. As a consequence of the fact that there is a sub-object corresponding to the Y implementation, this particular statement here will essentially bind the 2 pointer to the Y sub-object in this particular object here. And this is what's known as this is essentially what's known as the derived to base conversion. In other words, we can essentially get a pointer to base class to be bound to a derived class. Now here's the following observation that has to be made. As a consequence of the following proposition, we can analyze this particular statement here. We can essentially get a situation whereby the static and dynamic types can differ. In other words, the static type relates to the type and the declaration. In other words, we have a pointer to an object of type y. In other words, it points to an object of type y. That's what we refer to as the static type. But the dynamic type can actually, in reality, point to an object of another type. So we can get a situation whereby the static and dynamic types can differ. So that's the first point. Okay, so here's the next point. How does the virtual function mechanism actually work? How does virtual function... So we've considered various different details relating to the derived to base conversion. And we've discussed one of the direct implications of that in the sense that the static and dynamic types can differ. Now let's discuss how the virtual function mechanism works in relatively good detail, but we're not going to go into the details in terms of how it's actually implemented, the implementation techniques that make it possible, discussing, for instance, virtual function tables and so on. We're just going to be very abstract in our assessment and analysis and say there is some mechanism that enables the following behavior to take place. So here's the general idea. Let us first propose the following arrangement. Suppose we have, as indicated above, a pointer to an object of type y we'll call it 1 in this case, and we bind it to an object, the address of an object of type x. In that case, the static and dynamic types differ. Here's the general idea. Suppose that the class y is an abstract base class suppose the class y in terms of its implementation is an abstract base class that specifies various different pure virtual functions. Whenever you specify a virtual function in a class definition, it automatically invokes a process whereby we essentially insert a virtual function table, what's called a virtual function table, into the implementation of the class. We have a pointer to that in the representation of the class. And that essentially, we're not going to discuss in detail how that mechanism works because it's immaterial. We're just going to be very abstract in our analysis. So here's the general idea. Suppose we have a class of type y. We have a pointer to an object of type y, which is in and of itself an abstract base class, and we bind it to an object of a class type derived from that particular class type. And suppose that class type, the class type y in this case, defines pure virtual functions, and the class x, which is the type of this particular variable here, inherits from class y, and it defines specific implementations for those virtual functions. Well, here's what's going to happen. One second. Here's the general idea. What we can do is we can actually manipulate the underlying object to which x points through the pointer 1. And in that case, what we can do is we can invoke a particular function, which is a virtual function. We'll call it virtual. We can't call it virtual, we'll just call it virtual func. We can invoke what is a virtual function through the pointer 1. And in that case, what happens is, as a consequence of some abstract mechanism, the compiler and the system in general is able to resolve this call to the appropriate implementation as defined by the dynamic type of the object to which the pointer points. And so basically what we have here is a mechanism for the virtual, the, there's two things going on here. The derived to base conversion and the virtual function mechanism provides us with the capability to provide an interface class that can enable us to manipulate various different kinds of entities through that common interface class, and do so in a way that results in different behavior, because the various different derived classes implement different uh, instructions for the various different virtual functions. And so here's the point at hand. We return to the specification of the class query base, and we note that the destructor is virtual. And why is that the case? The reason that the destructor is virtual is to enable dynamic allocation of objects of this type on the free store. And the reason for that is as follows. As a direct consequence of the fact that the static and dynamic type of a pointer can differ, the fact of the matter is that we can have a situation whereby we have an object, a pointer to a particular class type, pointing to an object of a completely different but related class type. And in that case, we may very well dynamically allocate, we may very well have dynamically allocated that object on the free store and then call delete on the pointer to the base class type. And in that case, there has to be some mechanism to enable the invocation of the appropriate destructor. And so consequently, if the destructor wasn't virtual, there would be no mechanism to enable that to happen. So consequently, the destructor has to be specified as virtual in order to enable dynamic allocation of objects of type query base. Or just in general, I suppose, to enable typically any base class in an inheritance hierarchy has to define their destructor as virtual to enable dynamic allocation. So let us discuss the logical foundations of this particular code fragment. What's going on here is we're defining a common interface class that specifies that there's two things going on here. Firstly, we want to be able to manipulate various different kinds of entities relating to different kinds of queries through a common base class, which provides a common interface. And the second thing is we want to be able to customize the behavior whenever we invoke specific functions through that particular interface. So that's the desired goal of what's going on here. So again, this seems all without justification, and it's very difficult to see how this fits into the bigger picture until you see the larger context. And so consequently, we will move on to discuss the next part of our implementation. Okay, so the next part of our implementation is a class called query. And this is the class that is essentially going to act as the interface class to the complex inheritance hierarchy that we're going to define. We've already specified one component of that complex inheritance hierarchy. This class is essentially going to enable us to manipulate that underlying complexity through a well-defined and simple interface. In other words, encapsulating complexity and defining simple interfaces to interact with it. So that's the general idea of what's going on here. So we're declaring a class of type called query, and we will implement the various different components of it without justification, and then return to justify it in relatively shortly. But we'll discuss some of the logical foundations. So first thing we do is we need to declare three different functions as being friends. And in this case, we're overloading particular operators. So overloaded operator functions, we're going to declare them as being friends. And quite obviously, this is very simply because we need the implementation of those various different functions to access the private components of the query implementation. So we have to specify them as being friends. So the first friend function is the operator not. And as you can tell by the notation used, this has something to do with the not query. And that's all we know at this point. There's nothing else we could derive, practically speaking. And it has a single parameter. It is a unary operator, and so consequently has a single parameter. And that single parameter is a reference of type, a constant reference to a query object. We then have another friend function, which returns a query, and we're overloading the OR operator. And in this case, we need to specify two parameters because it's a binary operator. And in this case, it's constant references to query objects. And again, all this will make sense once we actually consider concretely the employment of particular notation. All this will become to make sense. But all we're trying to do now is implement it, and then finally return to actually reason about it in its totality. That's the general idea of what we're trying to do here. Another friend function, but we will allude to its logical foundations momentarily. And we're overloading we'll call it the reference operator, for the sake of simplicity. And it is a binary operator, and so consequently we need two parameters to represent that property, to reflect that property. Okay. Okay, so let us move on to the next portion of the implementation, which defines the public interface, as indicated by public access specification. And we have a constructor, as indicated by the name that we use, that takes a string. A moment. We have a constructor whose parameter is a reference, a constant reference to type string. And we can't define that yet. And in terms of the service that this particular constructor provides, we will return to discuss that momentarily. But for now, what's useful to know is its technical specifications. In other words, it is a constructor with a single parameter, which is a constant reference to an object of type string. Thus, it will be invoked in context whereby we supply a suitable argument for that parameter. Now, the next thing we need to do is, here's the general idea. The query class is intended to act as an interface to the complex and the relatively complex, but nevertheless simple, class hierarchy that we're about to implement. And so consequently, we need to implement our own versions of the pure virtual functions, but they're not going to be pure virtual functions. They're simply going to be regular member functions, and we will proceed to implement that immediately. That will actually perform a call to a virtual function. So in other words, it will delegate its work to another implementation. That's all the purpose of this function is. So the first is specification of a member function called eval, returning a query result, and we will extend the implementation of query result. We will propose an extension to it. We will perhaps not implement it, but the implementation would be trivial anyways. Called eval with a single parameter, which is an object of type TextQuery, which is that important abstraction that we need to keep in mind throughout the entirety of this implementation. And we'll call it T. It's a const member function, and we will define the implementation as follows. It will return the result of invoking the eval function on the thing to which the pointer q points, passing to its interface T. Now, this particular call here will actually be a virtual function call, because Q is, before we proceed to implement it, Q is essentially a shared pointer to an object of type query base. And we will actually return to discuss this momentarily, but shared pointer supports the same kinds of techniques as built-in pointers, in other words, the derived to base conversion. And so Q is the shared pointer to an object of type query base, through which we can, so in other words, we are attempting to define, we could systematically compose various different techniques in order to support the notion of representing various different kinds of entities within the representation of the query instance by means of some discrimination mechanism. But in our implementation, we're essentially defining a common interface through which we can manipulate various different implementations, that is to say, the various different derived classes. So that's the general idea. So we're going to be making a virtual call through the Q pointer, and Q is actually a shared pointer, but it has the same semantics as built-in pointers as far as the derived to base conversion goes, presumably because internally it represents the pointer as a built-in pointer. That would be the assumption, and then it just, by means of the automated specialized member functions, it just manages the lifetime of particular resources and so on. So that's fine, but this seems like it's without justification. So the only thing you need to keep in mind at this present moment is the fact that this is all we're doing is defining a member function with a particular parameter and a particular instruction. That's all we're doing. And we can't really tell anything more than that at this stage. We then define another member function, which returns a string. It's called rep. It's a const member function. And once again, it delegates its work to the object to which Q points by calling rep on the underlying object to which it refers. Next, we will discuss the private access specification. And in this particular case, we will have a constructor which takes a shared pointer to an object of type query base called query, and the constructor initializer list will set Q to query. And so consequently we need to suitably define, let me write that out again because it's very messy. We need to suitably specify what the Q data member is in order for this notation to be valid. And so we will do that now. In the private access specification, we have an object of type shared pointer, and to put it simply, that can point to a query base called Q. And then that's the end of our implementation for the moment being. We're going to have to come back to define the constructor once we suitably define various different other things. But let us discuss this implementation at considerable length. So the first point to note is that this particular So in terms of what the query class represents, the query class is an interface class to manipulate the underlying, to interact with the underlying complexity of the inheritance hierarchy. And so it's an interface class that hides that inheritance hierarchy. And as you can tell by this particular data member here, each query class will contain a shared pointer that points to an object of type query base, which essentially is equivalent to saying that it's going to contain a pointer that can point to various different kinds of derived classes. That's the basic idea. And we've already elaborated on other certain things. Okay, so the next point to note is that Uh, in terms of the friend functions, what are the friend functions going to do? Well, as you can tell, the specification of the friend functions returns a query. And the various, let's consider the not operator in particular. Uh, in terms of how we're going to represent the logic, encapsulate the logic of a not query, we're going to essentially derive it from query base. And so what's going to happen here is the implementation of this operator is essentially going to it's going to, one second. So anyways, the not operator is going to dynamically allocate an object of type not query. And it's going to assign the result to a shared pointer. And then we're going to, okay, so we're discussing details at this point. Let's just discuss abstractly what's going to happen. The implementation of this particular operator is going to dynamically allocate a not query, an object of type not query. Uh, uh, and what's going to happen? So it's going to dynamically allocate an object of type not query, and then it's going to return a query object bound to that particular dynamically allocated object. And so to do that, we essentially make use of the private, and this is why they need to be friends. This private constructor here, that's what we make use of in the implementation of the friend functions. Because what's going to happen is we're going to dynamically allocate, and again this seems very abstract at this stage, I understand that. We're going to dynamically allocate an object of type not query, and then we're going to store that in a shared pointer, and then use that shared pointer to construct an instance of type query. So in other words, it's going to invoke this constructor automatically in the return statement. And in that case, you can see that we specify the interface in terms of a shared pointer to a query base. And this is where we discuss the idea of defining a common interface. So in other words, we're essentially taking this dynamically allocated object of type not query to which a shared pointer refers, and assigning it to a shared pointer that points to a query base. And in that case, we have the derived to base conversion. And so consequently, what we end up with is a situation whereby Q, the Q data member, is essentially a shared pointer that will point to various different kinds of abstractions derived from the query base interface. That's the general idea of what we're trying to achieve here. So in terms of what they, let's see here, in terms of what this public constructor does, it creates a word query object, and we will discuss the implementation of the word query object shortly. In other words, it essentially creates a word query object and then stores a pointer to that in the Q data member. That's the general idea. And then of course we have the eval and the rep functions, and what they do will become clear in due course, but they're essentially mechanisms for actually invoking the underlying implementations for the objects to which the Q data member refers to, and that will make use of a virtual call, and that virtual call mechanism is enabled by what we will term as an abstract mechanism implemented by means of some technique that enables us to call a particular implementation depending on the dynamic type of an object, not the static type, the dynamic type, so long as the static type defines those functions to be virtual in and of themselves, such that there is a virtual function table that enables the mechanism to work. And also note that the actual version, in terms of the implementation of rep and eval for query, it calls a function on the underlying object to which the QData member refers to, and that's a virtual call, and so consequently it will be determined at runtime. That's what we call dynamic dispatch. Now, let us discuss, in fact, let me just say here, we'll perhaps skip this particular piece of the implementation. Actually, no, we'll discuss it. We'll discuss it. I was going to discuss it after because it's not necessary at this point, but we'll nevertheless, to keep it simple, we'll discuss it. So here's what we're going to do. We are going to define an overloaded operator which returns a reference to an object of type OStream, and the overloaded operator pertains to the bitwise left shift operator in the context of an expression whereby the left-hand operand is an object of type OStream and the right-hand operand is an object of type query. And very simply what we do here is we have a single return statement that uses the operator on the respective OStream instance to output the result of calling the query member function or the rep member function on the query instance. And that in turn will make a virtual call to the rep function on the object to which the underlying Q pointer refers to. And I suppose I'll discuss at this point what the rep function actually represents. The rep function represents a mechanism for returning a string that represents the kind of query that we're working with here. In other words, if we have an AND query, if we have, just to put it simply, if the call that ultimately is made here is a virtual function call to a function in the implementation of the abstraction representing the AND query logic, then in that instance, the rep member function will generate a string that represents the not only the operation being performed, but the operands of the operation. And so consequently, for instance, if the left-hand operand was, I suppose I'm going into too much detail here, but I will just say this. Suppose that internally it represented the left-hand and right-hand operands as word query instances, then in that particular case, the left-hand operand would essentially be a string representing a particular word, and the right-hand operand would be a string representing a particular word, and we would concatenate those strings together. But before we do that, we actually place in between them, and between the representation, the reference operator, or the ampersand operator, whatever you want to call it. And in that way, we can obtain a string representation of what the query represents. But we'll get on to discuss that relatively shortly. Let's see here. Let's go up to the top. Oh no, wait a minute. Okay, we'll start working here. So let's see, what's the next thing we need to discuss? So the next thing we're going to do is we're going to implement what we call the word query class. And we will return to justify, not only justify, but outline in terms of a diagram the inheritance hierarchy. But the next thing we need to do is we need to define a class called word query. And so we will proceed to do that as follows. Now here's the key. It inherits publicly from query base. And we already discussed the relatively simple implications of that mechanism previously. And we will specify the implementation as follows. A direct consequence of this inheritance is that the QData member of the query class can actually point to an instance of a word query because it's derived from query base. And here's the general point to note. Word query is going to override the implementations of the various different virtual functions so as to provide specific behavior. And that behavior can then be invoked by means of calling those virtual functions through the common interface class represented by the Q pointer in the query class so as to obtain desirable behavior. And you're going to see how all these pieces fit together towards the end. One second. Okay, so the first thing that we do is we make query a friend of this class in order to enable it to access the private components of the implementation. Because, by the way, in terms of there's actually, as I recall it, two distinctions between the class and struct mechanism. Apart from those distinctions, they are essentially the very same mechanism, perhaps even implemented by means of the very same code, in the sense that in terms of how the compiler actually treats these particular keywords, it essentially just invokes the same code with minor modifications that can be dynamically adjusted. But the general idea is that there's two distinctions between class and struct. I can't remember the second one, but the first one is that the default access specification for a class is private, whereas with struct it's public. That's one of the only differences. There is another difference, I believe. I can't remember what it is. And so, as a consequence of that observation, we can tell that the following implementation will be private by default. And so what we do is we define a constructor for word query with a single parameter, which is a constant reference to an object of type string called s, and the constructor initializer list will initialize one of the data members, which is a string, obviously. Well, not obviously, but it's a string. With s. So here's the general idea. We're going to move on to actually consider how it actually defines the virtual functions, the pure virtual functions that it inherits. So the first virtual function we're going to specify an implementation for is the one that returns a query result called eval. And again, I could discuss what this means semantically, but I think it's better to abstractly lay out without justification the implementation and then return to consider concrete notational employment in order to understand how all the pieces fit together. And so that's the approach I was going to take in this video. I was considering it for a relatively short amount of time, and that's the approach I thought was most interesting and most revealing. So we have the specification. We're providing specific behavior for the eval virtual function, which we inherit. And it has a single parameter, which is a constant reference to an object of type TextQuery called T. It is a constant member function. And I suppose one of the things you have to understand is that There are many different details in C++. Uh, the first thing you have to do is you have to prove that you can understand it. And the second thing you have to do is you have to retain the larger conceptual understanding of the various different language facilities, features, and components. And all the details are very important when it comes to implementing solutions because they have very important implications for the behavior of the program, which is obviously important. But I suppose the point I would make is that details like is the constness, I will pronounce it like that, inherited from a is the constness inherited from a base class? The assumption would be, logically speaking, when you analyze this code fragment, yes. But I suppose the point at hand here is that these details are immaterial. You don't need to remember every single detail so long as you have the ability to go back to a reference manual and look up that information and then implement a specific solution. So that's the specification of eval in terms of its interface. And it has a single statement, which is a return statement, which returns the result of calling the query member function on the T instance, passing query word to the interface. Now we know what's going on here because we've already specified the text query abstraction in our previous considerations, and we already know what the query member function does. And so consequently, it's easy to see that the query, in terms of what's going to happen here, is the query function is going to look at the representation of the text query instance, and it's going to make a determination. It's going to come to some determination as to the representation of the query result object it returns given the query word that we pass, and that in turn is going to be the result of this overall eval function. And so now we can see one of the first kind of pieces coming together. This will become clearer as we move forth. But here's a general idea. Now we have enough knowledge to state the following principle. If we have a query instance, the QData member of which points to, in terms of its dynamic type, an object of type word query, and then we call the eval function on the query instance, it will delegate its work to a call of the virtual function to the common interface. And in that case, it will make a virtual function call to this particular implementation, which will return a text query object synonymous with what the behavior we would get in our original implementation, and that will be the result of calling eval. So that's the first point to consider. Okay, so what do we next need to implement? We need to give a concrete definition for rep, which returns a string. It's a const member function. And the implementation returns query word, which is the data member, which we will move on to discuss very shortly. And by shortly, I mean now. So we define a data member of type string called query word. And that ends our implementation of word query. Again, we're just to reiterate, we are implementing without justification the various different components necessary to provide the behavior of evaluating complex queries on behalf of the user. Now, I was considering constructing a mechanism for being able to dynamically compose various different kinds of queries, but I wanted to do this lesson as soon as possible, and so consequently I didn't get round to that. But perhaps it is something that we could return to if somebody watches this ever. Just comment below, and then we will perhaps work on a solution to that problem. Because in our particular implementation, the queries that we will perform will be static. In other words, we can dynamically change the arguments to the various different query instances, the query constructors that create query instances, but we can't change the kind of query that it is. In other words, it's an AND query that's combined with an OR query that's combined with a NOT query and so on. There are various different techniques that could perhaps be achieved to achieve that, used to achieve that ideal, some of which are more systematic and perhaps not as efficient as others, but we will not consider that in today's lesson. So here's the next point. Now that we have defined the word query constructor, now that we have defined the word query class, we can define the query constructor that takes a string. And so we will do that as follows. We specify it as inline, and we will return to discuss. We already discussed that, I think, previously in the previous lesson, in terms of what that represents. We need to access the context of the query implementation, the query class, and we do that by means of this notation here, using the scope resolution operator. And we are defining the constructor that takes a string, and in terms of the constructor initializer list, we will initialize the QData member with a dynamically allocated word query, initialized with S. Now, as you can see here, we're initializing the QData member which is a shared pointer to an object of type query base with an instance of an object derived from it. And so consequently the static and dynamic types differ. So that's the first observation. So we have implemented that, and that's fine. Okay. Just considering what we need to do next. One second, let me just check this is recording. It is recording. Good. Okay. Now the next thing I would like to discuss is the following. So in the abstract sense, when we talk about NOT queries and AND queries and OR queries, these are queries with one or two operands. And in the case of NOT query, it's a single operand. In the case of the other two, they have two operands. And so the point to consider is that in each of those cases, in each of these classes, the operands of that particular abstraction can be any object of the concrete classes derived from query base. For instance, a NOT query can be applied to a word query and so on and so forth. And so to enable that mechanism, the operands must be stored as pointers to the base class query base. And so in doing that, we can bind any of those concrete instances to that particular pointer. But instead of storing a pointer to a query base directly in the representation, we'll instead use the interface provided by query itself in order to store the pointers to the various different kinds of derived classes. Let us move on to discuss the implementation of NOT query. Again, this is an abstraction that essentially encapsulates the logical service required that we would expect and require in terms of performing a not query as outlined in the specification of this particular section of the lesson. So, let us outline the implementations. We have a specification of a class called notQuery, which derives publicly from QueryBase, as we have already discussed, and the mechanisms and implications of which we have already discussed. And we make query, we make the following overloaded operator a friend. This is the operator that corresponds to the not query abstraction. And it's a single, it is a unary operand, so consequently it will only have a single parameter. And in this case, the parameter is a constant reference to an object of type query, and so therefore it will take an object of type query. And so the reason why we have to make this operator, overloaded operator, a friend is because it needs to access the private components of the class definition. That is, I suppose, a general reasoning as to why that's the case, but the specific reasons we will come to discuss. Let me rub this out. Okay. So the first thing we need to do is define the constructor. And so we do that as follows. The constructor has a parameter which is a constant reference to an object of type query called Q, and it initializes the query data member with Q. And that's all that it does. And this query data member essentially represents the operand of the not query abstraction. That's the general idea. As I said, we could have represented this directly as a pointer to the base class type, a query base, but instead we're using the interface class query in order to simplify the implementation of this particular mechanism, because that class is already built for that intended purpose. One second. Just one moment. I'm just reviewing something. Okay. So, we've defined this particular constructor. Let us now provide specific behavior for instances of this class type, particularly as it relates to the rep member function. And in this case, the implementation is as follows. we're returning a string, and so what we do is we build a string as follows. Now the way that, in terms of applying the what we would call the addition operator to built-in to string literals, one of the operands has to be an object of type string, and we achieve that by means of this right-hand operand here, which is the result of calling query.rep, and we already know what that entails. Let me just put the function call operator, and then we're going to add to the end of that a closing parenthesis, just to emphasize the grouping in terms of how the overall representation is evaluated according to the built-in C++ precedent rules. And that's the end of the implementation. It's as simple as that. Now, we're going to leave the eval functions, which are essentially the main substance of our query system, until near the end of the lesson. But for the moment, we have to specify its prototype. And so we will do that as follows. Very simply, it's a function called eval returning a query result with a single parameter, which is an object of type text, a constant reference to an object of type text query. And we don't have to specify a name for it, and it's a constant member function. And the last piece of the puzzle for this particular implementation is the fact that we have a data member of type query called query. And that's the end of our implementation of not query. So before we move on to implement the overloaded operator, let's discuss the rep implementation. In this case, we're calling rep on the underlying query instance. And that's going to be a non-virtual call, but that query instance in and of itself stores a pointer to the base class type query base, and it delegates the work. In terms of what it's doing, it delegates its work to a call to the rep function on the underlying instance to which the query base pointer refers, and so consequently it's going to make a virtual function call. And so consequently we're going to end up with a situation whereby this is a virtual function call that calls the appropriate implementation to obtain the appropriate representation of the various the derived type that the not query is operating on, because this is essentially to be considered the operand of the not query abstraction. So let us define the overloaded operator. We'll discuss. I said I was going to discuss inline before, but I forgot. But we'll discuss it in a second. So the overloaded operator returns a query and has a single parameter, which is a constant reference to an object of type query, and we'll call it operand. And it returns a shared pointer to a shared pointer to a query base object, which is initialized to point to a dynamically allocated object of type query, not query, as we would expect. Initialized with operand. And so now we can see why we had to make the overloaded operator a friend, because it uses in its return statement one of the constructors which is specified to be private, and so consequently we need friendship in order to alleviate that technical limitation. And in this case, what's going to happen is essentially what we're doing. What I would say at this point is this seems very abstract, And so the only thing to take into consideration is the technical specifications of what's going on and the logical implications in terms of the idea of derived to base conversions, virtual function calls, etc. The point at hand here is that, what was I going to say? We are, first and foremost, okay, we'll discuss inline in a moment, but we are dynamically allocating an object of type, we're dynamically allocating an object of type not query, the representation of which will correspond to the query instance upon which the operator was applied, and we're returning a pointer to that dynamically allocated object and then converting it to a query base pointer. And then it's a shared pointer, of course. And that the return statement implicitly uses a private query constructor that exists for the sole purpose of implementation, the implementation techniques we employ. And so that's, as a consequence of that, that's why this particular operator, overloaded operator, needs to be a friend of the query class in order to access that private constructor. But here's what I would say at this point. It's all very abstract. Just consider the technical specifications, and then you'll see how all the pieces come together at the end. In other words, what the purpose of this overloaded operator is. Okay, so let's move on to discuss the next piece of our puzzle. What we're going to do is so the next thing we need to do is we need to implement the abstractions corresponding to AND queries and OR queries. But we make one very crucial observation, and it is this. Both of those kinds of queries actually share one fundamental property that the others do not. And that is, well, the others do in the sense that the word query and the not, well, not, what, word query doesn't have an operand. So I suppose I will just disregard what I said. Here's the point. The AND query abstraction and the OR query abstraction, which we have just proposed and not yet actually defined, share one fundamental property with each other, and that is that they operate on the basis of two operands. And we can reflect that commonality by introducing another abstract base class to essentially hold the information corresponding to the different operands. And so consequently, and we will draw diagrams at the end of this lesson, well, essentially we will abstractly define this, what is an abstract base class, and we will see that in a moment as a consequence of the fact that it has a pure virtual function, a single pure virtual function in this case. We will see that we actually give a precise implementation for rep, the rep member function, and we will see how that is defined. But we inherit the pure virtual function and don't override it such that it becomes an abstract base class. So we have a specification of a class called binary query that inherits publicly from query base. One moment. Okay, so we have protected access specification, meaning that it isn't available to general users of the class, but classes that, to put it simply, classes that derive from this particular class can access the various different constructors and so on in order to actually initialize the representation, which we will discuss shortly. And so what we have is the specification of a constructor. I was going to write constructor there. What's it called? Query. Specification of a class called binary query that inherits publicly from query base. And we will specify its implementation as follows. Now, what am I doing? That is wrong. We're specifying the constructor. So, the constructor has a parameter which is a constant reference to an object of type query. And we'll call it L. And we're running out of space here. That's fine. That's fine. And another parameter which is a constant reference to an object of type query called R, and a string called S. And the implementation is primarily concerned with the constructor initializer list, within the confinements of which we initialize LHS, which is one of the data members, with L, RHS with R, and opsim, in other words the operator symbol, with S. And the purpose of that particular data member will become clear as we further elaborate on the implementation. So the next thing we'll do is we'll discuss the specification of the rep member function. We're going to provide a specific implementation for the rep member function. And so what it does is it returns a string. It's a member function, and it's const. So we are overriding the pure virtual function and providing a specific implementation for it. And it has a single return statement which does a series of concatenations. Is that how you pronounce that word, or is it concatenations? Anyways, concatenations. I think it's concatenations. And what we do is we compose an expression of the following form. Okay, we'll discuss that in a moment. Let me just do that to make sure that we have a distinction between whatever was written over here and what we're writing here. We'll return to discuss the rep member function in a moment, but we'll discuss the representation. We have two instances of query objects called LHS and RHS. And LHS corresponds to left hand side, RHS corresponds to right hand side. That represents the operands of the operator. Then we have an object of type string called opsim, and this essentially, in terms of its logical foundations, is supposed to represent the operator symbol associated with the abstraction. In other words, the specific abstractions that correspond to the AND query and OR query will use the protected constructors in order to initialize this representation, and the respective constructors will initialize the opsim data member suitably to correspond with the notation relating to the different abstractions. So for instance, the AND query will initialize it with the reference operator or the ampersand, and the OR abstraction will initialize it with the OR operator, and so on. Okay, so let us discuss rep for a moment before we move on. So again, this is one thing we have to observe here is that we've inherited a pure virtual function and haven't specified a specific behavior, and so consequently, uh, we inherit that pure virtual function, and that consequently makes binary query an abstract base class, meaning that we can't create any instances of it, but it defines a common interface common to various different derived classes, in this case AND queries and the AND query abstraction and the OR query abstraction. But let us discuss what rep represents. So we've already discussed okay, so in terms of what we've already discussed the fact that these particular data members correspond to the operands of the abstraction, and this particular operator corresponds to the symbol associated with the abstraction. And in terms of the rep member function, what it's doing is it's going to generate a string consisting of the representation of the left-hand operand uh, joined together with the operating symbol, joined together with the representation of the right-hand operand. Those function calls, respectively, this particular function call here and this particular function call here will make non-virtual function calls to the rep member functions of the query implementation, which in turn will delegate its work to a virtual function call through the pointer to the query base interface, such that it will ultimately execute implementations associated with the dynamic type of the pointer to which the queue data member refers to. And so consequently, we will get behavior that enables us to generate the appropriate representations for the operands concerned. So for instance, if the queue data member in the query instance pointed to an object of type not query, then consequently we would generate a representation that is appropriate for that abstraction. And so the left-hand operand would correspond to the not query, and we would be able to observe that from the representation, the string representation. And one thing you have to understand at this point, it's very abstract to understand that, is that everything's interoperable. It's a relatively simple program, but everything is interoperable. It's designed with careful consideration such that every kind of combination of the different abstractions is interoperable and results in desired behavior. And that's obviously a key design objective. Let me revert back to black. So is this the end of the implementation? It is. So let's move on to the next component. Okay, so the next thing we're going to do is we're going to implement the abstraction corresponding to the AND query, query and the OR query. So we will do that as follows. First we define a class called AND query. That publicly derives, for reasons we have already discussed in great detail, from binary query. Well, in this particular case, we have discussed it in considerable detail, which in turn inherits from query base. Of course, you have to understand that. Okay, so the first thing that we do is we make the respective operator a friend, because it needs to access the private components of the definition. And so we do that by means of the following statement. And the parameters correspond to the Okay, we'll just put a bullet point here to indicate that the grouping. The parameters correspond to the operands, and in this case it's a binary operator, and so consequently there are going to be two parameters. And the first parameter is a constant reference to an object of type query. We'll not name it. And the second parameter is a constant reference to an object of type query. Now, let me perhaps go over to the left a little bit, and that would be ideal. Now we define a constructor for AND query. Okay, we define a constructor for AND query, which has a parameter, and I suppose that the key observation here is that this constructor is only ever meant to be used in the implementation of the overloaded operator. And so that's not only why it in and of itself is private, but also why we make the overloaded operator a friend. And in this case, the first parameter is a constant reference to an object of type query called left. The next parameter is a constant reference to an object of type query called right. And the constructor initializer list delegates its work to the binary query constructor in order to suitably initialize its representation with left and right respectively. And we also pass the symbol reference operator, because that's the symbol relating to this particular abstraction. So in other words, the binary query models the commonality between the OR query and AND query abstractions in the sense that it represents two operands, and we represent that property by means of distinct data members in the representation of binary query, and we have to initialize that, and we do that by means of delegating the work of the AND query constructor to the binary query constructor, passing along the parameters involved. And this particular constructor in particular is only going to be used in contexts in the implementation of the overloaded function, the overloaded operator function. So, the key observation that has to be made also is that this particular class inherits the concrete definition of rep. So the next thing that we're going to do is we're going to define the prototype for eval, but we're not going to define it in the class definition. And of course it returns a query result. It's called eval, and it has a single parameter, which is a reference to a TextQuery object, I believe. Yes, it is. And we will neglect to name it at this point, and it is a const member function. Okay, so that's fine. So let's define the overloaded operator. And we're probably going to have to open another paint document very soon. So we'll finally discuss what inline means momentarily. I forgot to do that once again. So we're defining the overloaded operator associated with this particular abstraction. And let me just put a bullet point here just to make sure that we know this is all supposed to be. Well, technically speaking, as far as the compiler is concerned, it doesn't matter what form the tokens assume, so long as it can process them in a sequential fashion, and it is syntactically correct and so on and so forth. But for the sake of readability, we will assume that it is all in a single line. So, the first parameter is a constant reference to a query object called LHS, The second parameter is a constant reference to a query object called RHS, and the implementation very simply has a single return statement that dynamically allocates an object of type onQuery initialized with LHS and RHS and returns a pointer to it and stores that pointer in a share pointer to a query-based instance. And so we do that by means of the following notation. Specify, in fact, okay, we'll just specify it up here. Share pointer that can point to a query base. Put a bullet point here. Initialized from the result of dynamically allocating an object of type onQuery constructed with LHS and RHS respectively. And that's the end of our implementation of the overloaded operator. In terms of technical specifications, we can now see why there are various different friend declarations and so on. We now have an understanding as to why that's the case in order to access the private components of the query implementation and also the onQuery implementation and so on. And I suppose in terms of the logical foundations of what's going on here, the QData member in the query implementation points to a particular kind of abstraction that represents a particular kind of query, and that abstraction implements custom logic to perform the necessary actions to conform with the desired behavior that we would like to get in order to provide the semantics of and queries and so on. And so the point I would like to make is that what's going on here is that the LHS parameter and the RHS parameter, which is, again, you have to understand the notation that invokes this operator will be conventional notation. Notation whereby we specify a query instance constructed with some string, an AND operator, and another query instance constructed with some string. In that particular case, it will invoke this operator implicitly and perform the actions encoded within its implementation. And in that case, it's going to essentially, it implicitly uses the query constructor that takes a shared pointer and the return statement in order to construct the query instance. And I suppose what has to be understood here is that the onQuery abstraction relates to, it implements the necessary logic in order to provide the semantics of AND queries. And in terms of its representation, it must store a left-hand operand and a right-hand operand. And those two different query instances are what the operands are. And so, but we will get on to discuss precisely how it all works relatively shortly. We're near the end of this whole implementation. I'll tell you what I'll do. I'll put up another paint document here. Now, as a consequence of the fact that the logic underpinning the implementation of these different facilities is essentially the same, we will just speed run through the implementation so as to make this lesson a little bit shorter than what it otherwise would be. So, we'll just discuss this technical specifications. We're declaring okay, first and foremost, what does inline represent? Inline is a mechanism to essentially place the specification of the instructions of for instance, a member function, expand those, take those instructions, and essentially insert them at the site of the function invocation, such that you don't have the added computational cost of invoking a function, which implicit in its very nature involves a certain amount of computer resources. That's what the inline mechanism does. But I believe it is up to the compiler's discretion to determine whether or not it will inline a particular function, and it uses a certain set of algorithms in order to come to that determination, presumably. So I was going to say let's discuss the technical specifications, but I suppose we'll discuss the logical foundations to an extent. And that is that this particular class type is the abstraction that represents the logic of OR queries. And in terms of the technical specifications, we declare a class called OR query that publicly derives from binary query, which in turn derives from query base. And the implementation is relatively similar to previous. We make the respective function overloaded operator a friend to enable access to the private components. And the parameters correspond to the operands. And we will not specify the name for them at this moment. In fact, we don't need to do that. We can oh, no, we're clearly not defining this function. Let's terminate that statement as dictated by the C++ language specification. And let's get a rubber. So we're making the respective overloaded operator a friend. And then we specify that, again, this is all private by default. We specify the constructor as follows. And in terms of how the constructor works, it's analogous to how the AND query abstraction works. We have a parameter which is a constant reference to an object of type query called left, and a parameter which is a constant reference to an object of type query called right. And in the constructor initializer list, we initialize the representation of the underlying binary query subobject by means of the following notation. And the function body has nothing to do. Okay, that's wrong because we forgot the last argument. The symbol associated with this particular abstraction is OR, the OR operator. We'll call it the OR operator for the sake of argument. And the function body has nothing to do. And again, we're going to provide specific behavior for the query, for the eval function, which returns a query result. But we're not going to define it in class. We're going to come to define that in a moment. And I suppose at this point what I would say is that in terms of understanding what the eval function represents, it represents the logic that needs to be applied in order to provide the semantics of an OR query or an AND query or a NOT query, and so on. But we will see how that all the pieces come together relatively shortly. So the eval function returns a query result object, and it has a single parameter which is a reference to a TextQuery object, and it is a constant member function. And we will define specifically what that particular member function does relatively shortly. And then we define the associated operator, which returns an object of type query. We're defining the OR operator, the operands of which are a constant reference to a query instance called left. We'll call it LHS actually. The material, we could name it left LHS. And the next parameter is a constant reference to a query object called RHS. and it has a single return statement, which is essentially analogous to the previous return statement we considered, and so consequently need not be discussed in any significant detail. We have a shared pointer that can point, we'll indicate std here once again, a shared pointer that can point to an object of type query base. No, that's wrong. Query underscore base, initialized to point to a dynamically allocated object of type query, which is constructed from LHS and RHS. And I suppose at this stage, if you have a basic understanding of the C++ language, you understand logically what's going to happen here. In other words, this is going to invoke a constructor. We previously considered that constructor. We know that delegates to the binary query constructor, and so on and so forth. But all the pieces will come together relatively soon. Okay. Okay, let's move on to discuss the eval functions. So the way that these eval functions work is they call eval on their respective operands, and then they apply their own logic, and that logic relates to providing the semantics of AND queries, OR queries, NOT queries, and so on. In terms of how the OR query works, it returns the union of the results of its two operands. AND queries return the intersection, and the NOT query is a little bit more complicated. It must return the line numbers that are not on its operand set. So before we move on, we're going to propose an extension to the query result implementation that will be necessary to implement the various different procedures relating to the eval functions. And those proposed extensions are relatively trivial to implement, and I could implement them, although for the sake of argument, or for the sake of simplicity, we are not going to implement them, we're just going to assume their existence. And so what we're proposing is as follows. First and foremost, a query result has a begin and end members. It has begin and end members that will essentially return iterators into the set of line numbers associated with the query result. And the second proposition we make, the second extension we make, is that it has a get file member function that returns a shared pointer to the underlying file that represents the input file. Okay, 1 second, just try to review some material. Okay, so here's the general, in terms of, we talked about algorithms early on in the lesson, and what we're trying to do is we're trying to implement an algorithm that provides the semantics of an OR query. We're going to implement the eval function for the OR query abstraction first. And essentially what we do in terms of the implementation of the eval function is we call it eval, and again, the precise behavior that we get whenever we apply these various different uh, algorithms for specific inputs, the precise behavior we'll get will be discussed by considering a concrete example. But essentially what we do is we call it eval on the two operands that the OR query abstraction represents, and then what we do, those eval functions, again, you have to understand, it can get very complex in terms of the evaluation of the different kinds of queries, in terms of combinations of them. And so consequently, there may be several levels of nesting in the sense that a call at the top level to an eval function ultimately makes several calls to various different eval functions. But at the top level, essentially what's going to happen is we're going to call eval on the two operands that the OR query represents, and that's ultimately going to return a query result that represents the results of those particular queries. It's going to essentially return a query result, and then that query result contains information about not only the word that we were searching for, but the line numbers on which it occurs, and also a pointer to the file that represents the input file. And the job of, so in other words, this is relating to the logical model that we indicated previously, which is that the implementation of these eval functions is going to call eval on their respective operands and then apply their own logic. And in this case, the OR query eval function, in terms of the logic that it's going to employ, is going to return the union of the query results. In other words, to provide the semantics of an OR query, which is to say that we want all the different line numbers associated with either of the operands, we essentially have to apply logic to construct a set that contains all the different line numbers associated with both words. With the AND eval function, the AND query eval function, the logic is different because of course we have to return the intersection. And with a NOT query, we have to utilize a completely different logical structure in order to achieve the desired semantics. And so consequently what we'll do is we'll implement the OR query eval function as follows. So first and foremost, it returns a query result and we need to access the context of the OR query class. This should really be a larger row here. OR query class, and we do that by means of the following notation, and we're defining eval, which has a constant reference to an object of type TextQuery called text, and it is a constant member function. And here's how the implementation looks. Okay, so we employ auto-type deduction, the auto-type deduction mechanism, and I believe as a consequence of the fact that the auto-type deduction mechanism is implemented in terms of a theoretical invocation of an invented template type parameter, a direct consequence of that is that the types deduced for different variables and different initializations of different variables must be equivalent. And so in this case, that will prove to be the case, because the results will be query result objects. So we call eval on RHS, which is an object of type query, which will ultimately make a virtual call, and we pass text to the interface, and left is initialized with the result of calling eval on LHS passing text. Now, if you at this point, if you're still watching, do not understand this implementation at all, and even after watching the entire video still don't understand it, sometimes I find that you don't necessarily have to understand every single aspect of a particular program in order to gain useful insight. In other words, being a perfectionist can be quite detrimental. In other words, you can understand conceptually specific fragments of programs and gain useful insight in terms of how they are operating. And so the hope with the following code fragment is that that will be just the case. We just recognize the general and simple notion that we're attempting to construct a logical structure that enables us to obtain the union of the results obtained by calling the eval functions on the respective operands. And so we will implement that logic now. Okay. So here's what we do. We use the auto type deduction mechanism to declare a variable called retlines, initialized from the result of calling make shared, which essentially returns a shared pointer to a dynamically allocated object, I believe. 1 second. I'm pretty sure that's the case. I don't have to review that. But even if that wasn't the case, it wouldn't be the biggest deal. We're returning a shared pointer to a dynamically allocated set of integral values, and we pass to its constructor the result of calling the begin member function on left, and the result of calling the end member function on left. And essentially what we're doing here is we're utilizing the set constructor that takes an iterator range in order to essentially copy all the different line numbers, all the different integral values located in the query, in the set represented by the representation of the query result represented by... Okay, let me rephrase that. Essentially what we're doing here is, as you can see with left is going to be a query result object, and that's going to contain in its representation a set of line numbers that indicates all the line numbers that a particular word occurred on. And so what we want to do is we want to copy those line numbers, and we do that by passing this iterator range to the constructor. And so that's the first point. The second point I'll note before moving on to consider the rest of the implementation is that the set library facility does not allow equivalent value, duplicate values essentially, and so consequently the only statement we need to execute is the following one. We call insert on the underlying set to which retlines refers, and we 1 second, and we pass the iterator range denoted by the following. And this will automatically handle the case where there are duplicate values. No, that's wrong. Because the set implementation does not allow duplicate values. So we pass that iterator range, and then what we do is we return a query result representing the union of LHS and RHS. And so what we do is we have a single statement which returns a query result constructed from rep which essentially indicates the string representation of the particular query request. We pass retlines, which is the set that indicates all the line numbers that occurred on, and we then, it's immaterial, we could either use left or, assuming no ingenious mechanism to manipulate the different the shared state in terms of the vector that corresponds to the input file, and assuming no ingenious mechanism to make that be different for left and right, it is essentially material whether we use left or right in this particular the specification of the last argument, but we'll use left for the sake of simplicity. We call get file, and 1 second, let me just check. Get file returns a share pointer to the contents of of the file we're working with represented by a vector string. So that's what getFile does. And that's the end of our implementation. So I'm hoping at this stage that you're beginning to get a sense of how it works. You're beginning to get a sense of how all the pieces are coming together. And if not, don't worry, we will discuss a concrete example. We will discuss two concrete examples. I may make some mistakes, I may stutter and so on because I haven't actually prepared. I've prepared slightly for it. But we'll ultimately get the right answer. That's the main thing. Okay, let's implement. Before we implement the AND query eval, let me just review something. Okay, so let us move on to discuss the implementation of AND queries eval. In this case, it's going to return the intersection, and we'll utilize a particular standard library algorithm to obtain that result. So let's specify the implementation concretely. We have the specification of a function returning a query result within the context of AND query called eval with a single parameter, which is a constant reference to an object of type TextQuery called text, which is a const member function. Okay, so here's what we do. The first thing is analogous to the OR query, and that is that we essentially call eval, which ultimately results in a virtual call through the query operands to get result sets for the operands. So that's the first task that we must do, and so consequently we have the following declarations. One moment, that's wrong. We've already discussed what this particular function invocation does, and we also specify a variable called write, initialized with a return calling eval on behalf of the RHS instance, passing text to the interface. Okay, so here's what we do. We need a set to hold the intersection of left and right, and so we will declare that set right now. We'll automatically deduce the type from the initializer, and the initializer is the result of make shared, which will return a shared pointer to a dynamically allocated object. In this instance, a dynamically allocated set of integral values. And in this particular case, it's empty. Now here's the next component, and I'm not familiar with this function, so I'll be talking about it in the abstract sense. I looked at the specification, and it was fairly straightforward. It assumes some prerequisites and so on, but I am nevertheless unfamiliar with how it is implemented, and so consequently I will talk about it in the abstract sense. So what we do in order to obtain the union of results is we call a library function called setIntersection. and we pass iterators denoting the various different sequences, the sequences corresponding to left and right. That is to say, the iterator sequences corresponding to the sets to which left and right are objects of type query result, and they, in terms of their representation, store a pointer to a dynamically allocated set. I believe it certainly. I think it. Okay. It stores a pointer to a dynamically allocated set that stores a series of integral values, and we need to obtain iterators into that sequence that denote the entire sequence in order to provide the semantics required by this particular eval function. So we pass iterators into the sequence of the set stored in the representation of left. We do the same for right. And again, we have proposed that query result has these begin and end member functions, which will be relatively trivial to implement. And the last thing that we do, and I'll perhaps do it over here, is we essentially... Oh shit, what the fuck? No. We use this inserter function, and we pass the thing to which retlines refers, which is a dynamically allocated set, and ret an iterator denoting the first element in that dynamically allocated set. Okay, I did review this before, but just to be absolutely sure, I would just review a particular mechanism just to make sure that it will take no time at all. Just bear with me. One moment, I would just have to review. I think I know what it does, but I'm just double checking just to make sure I don't get anything inaccurate. And I suppose the key thing to understand is that it's an abstraction provided by the standard library to increase programmer productivity. One moment. Okay, I have located the particular page that I'm after. Okay, so essentially what this does, in terms of what's going on here, let's just analyze this particular argument. Essentially what we're doing is we're creating an iterator bound to the thing to which retlines refers, the implementation of which implicitly uses insert whenever we utilize the dereference operator, I believe. And the function takes a second argument, and that argument will essentially specify where to begin, where the elements are inserted, and the elements are inserted ahead of the element denoted by the given iterator. Now here's the point. This set intersection facility is just an abstraction. We need not concern ourselves with the details of how it works. The general idea is that it's going to enable us, it's going to look at the sequences denoted by, let me just enlarge that, the sequences denoted by the various different iterator ranges, which are sequences into the set of integral constants stored within the respective query results, and it's going to write to a destination iterator, which in this case is our empty ret line set, which is dynamically allocated. the intersection of the various different integral values. So that's the general idea. And once we've done that work, 1 second. Okay, we're good. Once we've done that work, we can return a query result constructed in the following form. First and foremost, we obtain a string denoting the string representation of the query abstraction. We pass red lines, which essentially denotes all the line numbers associated with. And again, I suppose I'll elaborate on this after. We pass a set which denotes the intersection of the respective sets in the respective query result objects. And then we pass, as indicated before, a pointer to the vector that represents the contents of the input file. Now, I suppose I should elaborate on what's going on here. In terms of what the query result represents, it represents the results of a particular query. And so at the top level, if the representation was such that it indicated that the notation used utilized the AND operator on two query instances, then in that case, whenever we print the result of query result using the print function specified earlier in the lesson, it's going to print that representation and then print the intersection of line numbers that both associated with both operands. And so in that case, we'll get a representation that indicates the kind of query that we executed, and then we'll get the appropriate results given what we would expect given the representation printed. And of course, we've already discussed what this last argument pertains to. Okay, we're not quite done yet though. Okay, just before I proceed, I will quote directly from my material here. In relation to the set intersection algorithm, the algorithm writes the elements that appear in both input sequences into the destination. So that is what it does. In terms of how it does that, it could utilize various different techniques in order to achieve that. But we'll not discuss that. Our goal is not to discuss implementation of the set intersection algorithm. It is to discuss the implementation of a query system that enables us to execute complex queries. Okay, let's move on to define the not query, which is it's relatively simple, but considerably more complex. And essentially the not query has to find each line of text within which the operand is not found. So let's define that concretely now. It of course, as always, returns a query result. We need to get into the context of the not query implementation, which we do with this notation. And we're defining a function called eval, a member function called eval, with a single parameter, which is a constant reference to an object of type text query called text, and it is a const member function, and we will specify the implementation as follows. So the first thing that we want to do is we want to call eval on its solitary operand, and so we do that by means of the following instruction. We declare a variable called result initialized with a return value of calling the eval function on the query data member, passing to its interface text. And again, it should be clear how all the pieces are coming together now. And what I mean by that is as follows. The eval query Suppose that in terms of the request that we make with respect to a query operation, we simply specify that we want to find every single, we want to invert a particular word in the sense that we want to find every single line that a word does not occur on. In terms of how that is represented, that is essentially going to, what's going to happen here is that query is a query instance, the shared pointer of which points to an object of type word query. And so consequently calling eval on that particular, making the virtual call to eval on that particular instance of query, this particular instance of query, is going to, oh crap, let me undo that. Okay, how do I stop that? It's going to make a virtual, okay, I was distracted by that. Okay, let me restart again. So, if we had a single solitary request, which is to say that we want a not query, we use the not query abstraction on a particular word, then in that case, the query data member corresponding to the not query instance will in and of itself contain a shared pointer to a word query instance. And so consequently calling eval on that query instance will make a virtual call to that particular implementation as indicated by the word query implementation, which very simply in and of itself does the normal processing that we specified in our initial implementation and returns a query result indicating all the lines and so on, and the word in particular that a particular word was located on. And so we essentially obtain a query result relating to that information. And so the following logic can be seen as applying the necessary steps in order to obtain all the line numbers that a particular word was not found on. I hope that helps in understanding the logic that's about to be outlined. And so consequently we will proceed to outline it. So once again, we start with an empty set. Okay, I need to make that stop. Is it still doing it? Okay, it's still doing it. Okay, that's an A. So first and foremost, we need to start off with an empty set. So we declare a variable of a type specified by the initialization portion of the declaration called redLines, and it's essentially going to initially point to, it's going to be a shared pointer to a dynamically allocated set of integral values. That's the using declaration that we specified earlier. And we don't pass anything to its constructor because we want the empty set. Okay, so the next thing we want to do is we essentially want to iterate through the lines on which our operand appears. And so consequently we want to obtain iterators into the particular set stored in the representation of the query result instance, which is represented by result. And so to obtain iterators into that particular set within the representation of the query result, we declare a variable called beg, which denotes beginning or begin, initialized with the return of calling the begin member function on the result instance, which is a query result, which is essentially going to give us an iterator denoting the first element in the set stored in the representation of the query result instance. And then we want to obtain an iterator to one past the last element in that sequence, which we achieve by means of the following initialization. Okay, 1 second until I review this. Okay, 1 second actually. I'm just reviewing the material. Okay, let's proceed to implement this. So the first thing that we want, essentially what we want to do, is we want to create a structure that enables us to iterate through every single element contained within the iterator sequence denoted by beginning and end. These particular bag and end, I should say. We want to iterate through each value within that particular iterator sequence, or iterator range. And we essentially want to ask the question, if the value to which the iterator currently refers to, and we will be using the increment operator on the beginning iterator, if the value to which that iterator refers is one second. I actually just have to carefully consider this before I articulate it. Okay, we can proceed. Okay, so the first thing we need to do is, essentially what we're attempting to do here, is we're attempting to iterate through the iterator range denoted by bag and end. And we essentially have to check whether or not the integral value represented by the iterator that the value to which bag currently refers, we have to check that that is not equivalent to, actually 1 second, just to review this. Okay, so essentially we're going to employ a looping structure to check. We're going to in fact, let's lay out the implementation because it's slightly nuanced. That's why I had to take a little bit of time there just to make sure that I fully understood what was going on. It's relatively simple, but I just have to be sure of these things. And so let's lay out the implementation, and then we'll discuss it in detail in terms of what's going on. So the first thing we need to do is we need to obtain the size of the input file represented by the vector of strings. And so we can do that by means of the following initialization. Result represents a query result instance that stores that input file in the vector of strings, represented as a vector of strings. And we call get file on it to obtain the shared pointer to that particular vector representation. Then we use the arrow operator to obtain the size of that particular vector. Now, here's what we do. So we've got the size. How does it fit into the picture? We employ a for loop, the initialization portion of which declares an object of type size t, which is an integral type, implementation defined, initialized to 0. The target expression checks for its inequality with SC. In other words, in terms of how a for loop works, essentially there are 4 different portions of it. There's an initialization portion, which is this portion. There's a target expression, which is this portion. There's the loop body, which is essentially going to be located here in a moment. And then there is an action portion, which is located here. In fact, I'll fill in the action now. And that is fairly simply an incrementation of n. In terms of how the for loop works, it performs the initialization portion only once, and then it tests the target expression. If it evaluates to true, we execute the instructions encoded in the loop body, and we perform the action, which in this case is an incrementation of n, and then we don't perform the initialization portion again, obviously. We perform the check of the expression once again. We check for its Boolean validity, and if it still evaluates to true, we execute the loop body once again, and we repeat so on and so forth until the target expression evaluates as false. So that's how a for loop works, and it's a fairly basic structure, but very powerful. Also note that I was going to write, just as a side note, I was going to write a paper. I'm going to be writing a paper detailing my particular formalism of the C++ programming language, and I detailed that at the start of the lesson. And I suppose one of the points I was considering in relation to that was that, except for not considering at the lowest levels, in other words, generated machine code and operating at the lowest levels of a system, disregarding that for a moment, in theory, any logic that can be implemented in a for loop can be just as well implemented as in a while loop. And so consequently, one asks the question, what is the purpose of the for loop? Why ever introduce such a looping structure if every single logical use of that particular looping structure can be achieved by means of this of a while loop? Why implement or introduce the for loop facility? And I suppose the only answer I could come up with, at least from my knowledge base, is that the for loop is a very powerful mechanism in the sense that it groups together sets of related information. In other words, in a while loop there would be what is ostensibly an unrelated declaration before the while loop was encountered, and so consequently, readers of the program would perhaps not be able to reason as well about the termination conditions of the while loop. Whereas with a for loop, all the information in relation that relates to the termination condition and the actions that are performed on the Boolean condition, or the expression we check for its Boolean validity and so on, that's grouped together in a single logical construct. And so consequently, it provides a powerful mechanism for expressing a solution whereby you want to group sets of related information into one entity. So that's the purpose of a for loop, but that's unrelated, to be honest. But we will write that paper and we will present it relatively shortly. I'll perhaps elaborate on that at the end of the lesson. So here's the logic of the implementation. Basically what we say is, if beg is equivalent to end, in other words, if we have reached if after repeated incrementation of the iterator denoted by beg, if repeated incrementation of that results in a situation whereby beg is equivalent to end, in other words, we have iterated over every single element in the iterator range, or the thing to which beg refers is not equal to n, the action we want, and we will discuss this particular statement here. I was just trying to reason about it, and we will discuss it at length. What we want to do in the situation whereby, first and foremost, we've discussed this previously, but the logical OR operator has short-circuit evaluation, so consequently, if this determines the result of the expression, we won't even consider this. But if the entire expression if this entire expression in its entirety, I should say, evaluates true, then essentially what we want to do is we want to call the insert member function, on the object to which readlines refers, no, that's wrong. In order to insert the value of n, which is an integral value. Now, readlines is we're essentially dynamically constructing the set that relates to all the line numbers that a particular word was not found on. And that's what this particular for loop achieves in terms of its logical foundations. Else, in other words, we have an else branch here, and we have to explicitly check for the following condition. Explicitly check the following condition. Else we say if beg is not equal to end, increment beg. Okay, so here's how this is working. So essentially what we're doing here, and you'll notice, I suppose, as a consequence of the introduction of this particular branch of the if construct, essentially what we're doing is we are looking at the value denoted by beg. There's an observation here that has to be made in order to understand what's going on here. The set implementation stores its elements in an ordering determined by the less than operator in terms of the default semantics. And so what we're essentially trying to achieve here is we're essentially we're looking at, one second. Just consider this particular statement. Okay, so just consider this particular statement here. What we're essentially checking is if the thing to which beg refers to, which is an integral value, is not equal to n. Now, if that were the case, then the implication is such that in terms of the way the set implementation stores its elements, if the thing to which beg refers is not equal to n, that means that we need to insert that particular integral value into the set that we dynamically allocated on the free store. And so in that case, what we do, it's all about understanding how the set implementation represents the sequence of values. In that particular case, we don't want to execute the statement. We still want to consider that particular iterator. And so what we do is we discard this particular statement, or this particular branch of the if construct here, and we iterate once more. And essentially what we're doing is the central data in this looping structure is n. In other words, we're checking if the thing to which beg refers to is not equal to n, and as long as that's the case, we insert that value into the dynamic set, the set that we dynamically allocated, and we keep doing that until either this condition of values is false. We essentially keep doing that until this condition of values is false. But at some point, it may be the case that beg is incremented to such an extent that it becomes equivalent to end, and in that case, logically speaking, we need to add every single subsequent value of n located in the range from that particular iteration to up to the value sc. I think that's probably rather abstract, so I suppose what we could do is we could actually look at a concrete example of this. So suppose that we had a vector of strings representing the input file, and it had, let's suppose, 6, no, not 6, what am I saying? I missed out 2. It had 6 elements. And suppose we conducted the query operation and obtained the result that yielded a set that contained the values 1 and 3. In other words, this set here, in the abstract sense, represents the set of line numbers that a particular word was found on. And the job of this particular for loop is to implement the logic necessary to form a set that consists of every single value within this particular set of numbers that doesn't contain any of the values located in this set. And so, in terms of how what happens is, n is initialized to 0. We check if n is not equal to SC. SC is equal to 6 in this case. 0 is not equal to SC, evaluates to true. And then what we say is, if beg is equal to n, that's not true. But if the thing to which beg refers to is not equivalent to n, in other words, the thing to which beg refers to is 1. If it's not equivalent to n, which in this case is 0, now it just so happens that the current, let me just think. Okay, so essentially what we can regard, these are the values of n that we're going to iterate over essentially. Okay, that's simple enough. So we check if the thing to which beg refers to is not equal to n. In other words, is 1 not equal to 0? That's true, and so consequently we execute this particular statement here. So essentially we form another set that contains the value 0. Now notice that we discard this branch of the if statement, and so consequently we do not increment f, or increment beg. And so we iterate once more, we increment n becomes 1, we check if 1 is not equal to 6, that is the case. If beg is equal to n, that's false, or if the thing to which beg refers to is not equal to n. Now let's look at that. The thing to which beg refers to is equal to 1, and n is equal to 1. In that case, they're equivalent, and so consequently this evaluates to false. And this obviously evaluates to false, and so consequently we do not execute this statement here. And so consequently what we do is we consider this particular branch, and we check if beg is not equal to n, which is the case, we increment beg. And so consequently beg now refers to number 3. The value to which it refers is number 3. We increment n once again. We'll just go through this to be very verbose about it. We increment the value of n such that it is now 2. Is 2 not equal to 6? That is the case. We check if beg is equal to n, that's not the case. In fact, oh no, that isn't the case. N would conceptually be located here. We check if beg is equal to n, that's not true. If the thing to which beg refers to is not equal to n, in other words, 3 is not equal to 2, that is the case, so we add 2 to our new set, and we discard this particular branch. We then increment n, it becomes 3. Is 3 not equal to 6? That evaluates as true. Is beg equal to n? That's false. Is the thing to which beg refers to, which is 3, not equal to n? In this instance, n is 3. That's not true. And so consequently, we execute this branch of the if construct. We check if beg is not equal to n. That is true, so we increment beg such that beg now refers to this location, conceptually, and then we increment n. Now in this case, beg is equal to n, and so it will unconditionally add each integral value subsequent to that to the set. And in that way, we obtain a set that represents all the different line numbers that a particular word was not located on. Now I've messed up my implementation here, but it ended quite simply as follows. We constructed that set and then we returned a query result constructed from the appropriate data. Representation, the string representation of the kind of query, red lines, which is the dynamically allocated, is a pointer to a dynamically allocated set, and then a pointer to the vector representing the contents of the input file, which we obtain as follows. And that's the end of our implementation. One second, just to review the material. One of the key observations, though, that enables this particular loop body to work is the fact that the set stores its values in ascending order, as indicated by the less than comparison criterion. One second to just review the material. Okay, so that's it. We have implemented every single component that is necessary to provide the service of executing various different what I call complex queries. In other words, we have implemented all the various different components that are necessary to allow the initial notation that we considered. So in other words, I suppose what I'll say is that we have devised a relatively simple, but it's relatively complex inheritance hierarchy. And we have defined a simple interface to that inheritance hierarchy represented by the query class. And we can thus construct complex queries of the form. So we would declare a query object called Q. And if we wanted to perform an AND query, we would utilize the following notation. Okay. Just one second, just to double check. So to actually evaluate the query, we would use the notation q.eval, which is a non-virtual call, and we would pass the TextQuery object that essentially encapsulates the service of querying the contents of the input file, because the constructor automates the process of building a lookup map and so on. So with it, in other words, what we have done is, and this is really one of the characteristics of the C++ language that I will discuss when I consider the matrix implementation, is that its expressive power is awesome. You can define a great deal of complexity and define an interface to it that is so simple and intuitive, such that it results in notation like this. Everything that we have built, all the components, every single implementation, function, facility, library facility, etc., results in an end product that enables us to use the following notation to execute operations of fundamental importance, like the semantics of an AND query. Okay, so the last thing that I'm going to consider, let me just check, have I covered everything? Okay, so I think what I'll do first is I will consider a concrete employment of a particular notation, and then I will discuss the design process that led to this implementation. and so on and so forth, the design considerations that led to it. But I'm going to stop recording now just so I can I don't want to get this wrong and blabber and incoherently ramble, so I will just quickly review uh, the necessary material, and then we will discuss a concrete employment of certain notation and understand precisely what's going on in terms of logic. Okay, so I took some time to evaluate the precise logic surrounding the relating to the evaluation of particular complex queries is what I will refer to it as. And so the general point that I would like to make is that let us get another paint. In fact, okay, we'll operate within this paint document. The general point that I would like to make here is that we proposed in our initial considerations that we would like to construct an implementation that would enable notation such as the following. And we will discuss this at length momentarily. And finally, this is what I would call a complex query. In other words, not only is it utilizing the AND query abstraction mechanism, but it's also utilizing the OR query abstraction mechanism at some point in some way. And the program is very robust in the way that it deals with these kinds of requests. Now, before I proceed, as I was talking about earlier, I was considering implementing a solution that would enable us to dynamically create certain kinds of complex queries to match the user's intent instead of hard coding the different kinds of combinations of complex of queries and so on into the source code, and then giving the user the ability to dynamically assign the strings that are passed to those to the query instances and so on. But I decided not to do that because, quite frankly, I wanted to do this lesson as soon as possible for various different reasons. And so, here's the point at hand here. Our initial considerations were concerned with constructing the appropriate implementation that would enable us to write expressions like this, and then write something equivalent to the following. Of course, we could encapsulate this added complexity in a function, for instance, or an overloaded operator in order to provide notational convenience to make this entire process more abstract and thus more friendly to the general user. But in this case, we would pass the text query instance that relates to the lookup map that actually contains in its representation the lookup map that associates each word with a set of line numbers that it appears on and so on in the input file. And of course that text query object in and of itself contains a shared pointer to a dynamically allocated vector of strings that represents the entire input file and so on. But here's the point. Our initial considerations were concerned with constructing the appropriate implementation that would enable us to write something like the following in order to perform fundamental operations relating to complex queries into the contents of a particular file. Now note, this particular segment here, I'll outline it in purple, constructs a set of interrelated objects, and this particular expression here actually performs the evaluation on the particular text query object. So in other words, this particular segment here essentially defines the skeletal structure, the substantive base upon which we supply further information in order to get results that we desire. And so I suppose what I'm going to consider now is we began by saying that we weren't going to justify the implementation, we were just going to present it. And then at the end, not only were we going to justify the implementation by deriving the design considerations that led to the implementation, or at least fragments of the implementation. Of course, an implementation as complex as this wouldn't necessarily be reflected in all design considerations. But the point at hand here is that not only was I going to discuss the process by which we came to the conclusions relating to how we implemented the solution, but also to make what is perhaps very abstract concrete by actually inspecting precisely what happens in expressions such as these. In other words, what's happening in this kind of expression. So that's what we're going to do next. So let's write out the expression once more. Here's the idea. We're declaring an object of type query called Q, and we're initializing it with the following value in the abstract sense. Let me just undo that. Actually, I'll rub it out. And we will discuss this notation shortly. Okay, so the point at hand here is that whenever we define all these various different components and package them into some library for end users to use, the instructions manual would essentially say, whenever you want to construct a specific complex query, you use notation equivalent to the following. You construct query instances with particular strings, and you use the various different operators in order to express the complex query that you're trying to achieve. And then the result is stored in terms of what's generated by this code, the result is stored in a query instance called Q, and then we can use this notation here in order to extract the query result associated with the complex query. Of course, we could further simplify the life of the client user of the library by implementing an overloaded output operator that automatically handles this extra step, which in some sense exposes implementation details, which is something to be avoided in libraries that are supposed to be as abstract as possible. But here's a general idea. We want to consider what's going on in this particular statement. Note at the beginning, and by the way, this operator here is the OR operator. So remember at the beginning, what the hell? Remember at the beginning we said that the queries themselves will be evaluated according to C++'s precedent rules. In other words, the built-in precedence levels for the various different operators. And so taking that into consideration, let us analyze what's going on in this particular segment of the code. What's going on here is as follows. I'm not quite sure about the precedence levels of the OR operator and the AND operator, but they are at least equivalent. Let's suppose, for the sake of argument, they are at least equivalent. Let's get a different color here. In that case, so let's get into the substance of how this is evaluated. In that case, we need to evaluate this particular segment of the code first. And this particular segment of the code, in order to evaluate it, will involve, in terms of what we know with the benefit of hindsight, it will involve the invocation of an overloaded operator, the overloaded reference operator, but I suppose in the general sense it would obviously at some level involve the invocation of some unit of computation that specifies what to do in the context of expressions whereby the left and right hand operands are objects of type query. But what's going on here? The application of this operator on these operands means that we're going to have to invoke some unit of computation. But in order to do that, we have to actually evaluate the operands first. And so consequently, the order of evaluation is unspecified, I believe. But let's suppose that it evaluates the left-hand operand first, this operand here. What's going to happen in that case? Let me graph it out and then we'll justify it by actually inspecting the implementation to prove that that's what's going on. So we're analyzing, just to be concrete, this particular sub-expression. Okay. So when we evaluate this left-hand operand, what happens? It creates an object of type, in essence, it creates an object of type query, the representation of which points to a word query. And we will justify that now. So let us go to the constructor that takes a string for query, and we will walk through it. I believe it was I think it's in here. No, it's not in here, is it? It's in here. Okay, this might take some time to find. I think I know the order that it was done. Okay, so here's the constructor. Let me highlight this with a different color. Here's the constructor that's invoked in that case, and so consequently we need to locate its definition. Where is its definition? Go up here. It's down here somewhere. Okay, so here's its definition. Here's what it's doing. This particular constructor, which accepts a string, sets the QData member, and we could inspect. You can go back and in fact, it will probably be helpful just to look at the QData member, just to make sure that we understand what's going on here. The viewer understands what's going on here. The QData member is here, and it's a shared pointer to an object of type query base supporting the same kinds of operations as built-in pointers in relation to static and dynamic type difference. So it invokes this constructor, and that constructor in turn initializes the QData member to point to a dynamically allocated object of type word query initialized with S. So consequently, we end up with a situation whereby we have a query object, the Q pointer of which is a shared pointer, is pointing to a dynamically allocated object of type word query, which is inherited from query base, and that object in and of itself is constructed from S. So let us go and look at the definition of that particular constructor. So the word query constructor that takes a string. Let me just reposition my pad here. The word query constructor that takes a string sets the query word data member to S, and that's all it does. Okay, let's return to this point. So we have justified this particular graph here. Let's choose another color. The evaluation of this operand will be analogous. In other words, it will create a query instance, the representation of which points to a word query. Now, Because we have evaluated both operands, we can actually proceed to invoke the appropriate function in order to evaluate what this particular sub-expression should mean. And in this case, we have a situation whereby the left-hand and right-hand operands are of type query. And in that instance, we're going to invoke the overloaded operator that we specified that operates in terms of operands that are of type query. And so let us try to locate that. I think it's in here somewhere. One moment. So we're looking for the AND. Second, let me just locate this. No, it's not going to be in here, is it? I think I'm looking in the wrong file. I was. Okay. Okay, so here's the overloaded operator. Right here. So what does the overloaded operator do? The overloaded operator accepts the left-hand operand as a reference, the right-hand operand as a reference, and what it does is it dynamically allocates an object of type AndQuery initialized with LHS and RHS. And we will proceed to analyze what this particular expression is doing here. But what we're trying to observe here is that this expression essentially dynamically allocates an object of type AndQuery, and we pass to the constructor's interface LHS and RHS, which corresponds to references to the query objects that are the operands of the ampersand operator. And we have a shared pointer to that, which is a shared pointer to a query base. And then we return that. And the return value of the function is a query, and so consequently it will implicitly use the query constructor. And a graphical representation of what's going on there is as follows. So it's going to use the query constructor with the interface of which is a shared pointer to a query base. And again, I think I indicated this at the beginning. The way I talk about this as being a shared pointer to a query base. But if we were being general, we would say shared pointer instantiate with query base. But semantically we wouldn't be able to derive much from that. So consequently, we say shared pointer to a query base. And for the sake of illustration, we'll just name the parameter x, and it does something. Now here's the key. We pass to that constructor a shared pointer to a query base constructed from a dynamically allocated AND query initialized with LHS and RHS. Those are the parameters of the overloaded function operator. Now let us, I suppose, I wasn't going to do this, but we'll go into details in terms of what's happening here. We're creating an AND query object and passing LHS and RHS. So let's go to AND. As we can see, the constructor that takes a query object, two query objects, simply passes the binary query left and right, and that in turn essentially suitably initializes the representation of binary query such that it contains two query objects corresponding to those query instances. And we can see that action being performed here. And we also pass the operating symbol. Did I write that? 1 second. Yeah, I did. So there's the operating symbol. So we pass we essentially delegate the work to the binary query constructor, which initializes its representation and so on, which is here. And that's the end. So, with all that in place, let's suppose for a moment that we were only considering this particular sub-expression here, not including the OR operator. In that case, we would essentially obtain a query object, because remember, the overloaded operator is returning a query object. We would obtain a query object, the representation of which, well, we'll discuss that in a moment. Essentially what we do is we obtain a query object and we assign that to Q. And then we can use the notation q.eval, and here's where we pass the TextQuery object instance. And if we wanted to record the text, the query result associated with that, calling that eval function, we would write something akin to the following. So here's the crucial thing to understand. What we're doing here is we're calling eval on Q, passing TQ to the interface. What does that do? Well, we're calling eval, which is a non-virtual function in the implementation of query, which in turn makes a virtual function call to the eval implementation specified by the object to which the Q pointer points. In this case, it points to an onQuery object. And so let us justify that by considering all the steps that are necessary to get to that point. So let us go over here. So where's eval? There it is there. So here's what's key. We're passing around this TextQuery object located here. And what does it do? It returns the result of calling eval on the object to which the Q pointer points. In this case, it points to an object of type onQuery, and so consequently we're going to execute the instructions associated with the onQuery's implementation of eval. So let us go to look at that. Okay. One second, I'm just okay, so here's the I was just thinking there. I thought I heard something. Anyway, so here's the specification of the prototype for eval, but we don't actually implement it in this file. So we need to actually go in and assess what that's doing, which is in this file, this notepad document. Okay, so here's the key. Wait a minute, I don't okay, that's fine. Okay, so here's the onQuery eval. Now, we make a virtual function call through the Q pointer to the eval implementation specified by onQuery, because that pointer is actually pointing to an onQuery instance. And in that particular case, the onQuery instance maintains two data members, LHS and RHS, upon which we call eval. Now what's going to happen in that case? In that case, the query instances stored in the uh, portion of the object that is an AND query, in particular the binary query, that's going to be a regular query object. And so consequently, we're calling eval on a regular query object, which in turn has a representation that points to a word query, I believe. Hold on, let me just check that. One second. Which file am I in? Okay. One second. I'm just. Okay. Anyways, so what are we looking for here? It creates a. Okay, so the query instances point to word queries, the implementation of which, uh, in terms of its representation, is initialized with uh, its representation contains a particular string. Okay, that's fine. Now we call eval on the query instance. That query instance, in and of itself, in terms of its Q pointer, points to a word query in terms of its dynamic type, and so consequently we're invoking the eval implementation of the word query. What does that do? Well, we will see what that does. So where is word query? Okay, so the eval function, fairly simply, and again, remember we're passing along this text query object every time we invoke a function, every time we invoke eval. It very simply returns the result of calling the query member function on the T instance, passing query word. And we know what that does because we considered it in our initial simplistic implementation. What's that going to do? This expression here returns a query result. That means it returns a query result as specified by this particular specification. And if we go back to here, left is going to be a query result and right is going to be a query result. And in terms of what's happening here is we essentially have obtained two query results that relate to that contain all the information necessary in order to begin formulating an end product, that is to say the final query result object. In other words, what we need to do next is we need to essentially taking into consideration left and right, we need to construct a set that contains the union, no, the intersection of the different integral values stored in the respective sets and in those query result instances. And so the rest of this implementation does just that, and then it returns a query result, and it calls rep, and in this instance, in this case, rep is going to return, remember rep was defined in the binary query specification, and in this case it's going to return, let's just go back and analyze that. Where? I think it's over here. Okay, so as you can see, the rep is going to be generated by calling rep on the LHS instance. And so that in turn, that's calling rep, that's a non-virtual call to rep, which in turn is going to make a virtual function call through the pointer q to rep to the appropriate implementation. In this case, q points to a word query. And so we go and inspect word query. Oh, it's not in here. Is it? What is? we go and inspect word query and see what its rep is doing. And it fairly simply, as I can remember, it returns the string. So it just returns the string query word stored in its implementation and its representation. So we can go back over here. So consequently, it's going to return the string stored internally in the word query instance. And then it's going to concatenate the operating symbol, which in this case is the ampersand. And then it's going to do the same process for the RHS parameter. And that's fine. So now go back to here. We generate the rep. And in this instance, we essentially have a situation whereby the rep would be something like 1 and 2. So the rep would be that. Red lines contains the line numbers in terms of the intersection of the line numbers that both of those words occur on with respect to the TextQuery instance that we passed along to the various different implementations. And then we have to pass the pointer to the vector storing the contents of the input file. And in that way, we generate a query result that we pass back along all the various different function invocations. I can't quite remember where we left off. Oh, so we were analyzing this. So essentially what we obtain is, or no, we were assessing this particular, the evaluation of this particular expression, I believe. So essentially we obtain a query result instance that contains all the necessary information given the query that we were trying to perform. And then we considerably print that information. Now, if that's all we were considering, that would be fine. But we have this additional OR operator here. And what I will do is I'll not necessarily go through the implementation. If you need help, basically what I would recommend is that you remember or write down the various different implementations and go through this process yourself. I could do it. It's relatively trivial, but it's very time consuming. And so I'm not going to do that. But what I will do is outline the general principles in graph form. So, we're not just stopping there. Let's go back up here. The evaluation of this particular sub-expression yields a query instance. And that query instance contains a pointer called Q, pointing to a dynamically allocated object of type query that stores, in terms of its representation, what are conceptually the operands of the operator. Now, here's the important point to note. The result of this sub-expression is a query object in and of itself. We need not concern ourselves with the details of its implementation at this stage. Just note the following. The left-hand operand resolves itself to query. We have the OR operator, and the right-hand operand resolves itself. Well, it doesn't resolve itself just yet. We have to evaluate it. So that's the right-hand operand. And we need to evaluate this. And when we do that, we obtain a query, the representation of which points to a word query. Very similar to our previous considerations. Now, the representation of this points to an AND query object. Now, here's the crucial thing. Essentially, what we do is we evaluate both operands of this particular operator, and that's going to invoke the appropriate implementation, which in this case is the overloaded OR operator. And the overloaded OR operator is going to return a shared pointer to a query base which points to a dynamically allocated object of type OR query initialized with LHS and RHS. Those are the parameters of the overloaded function the overloaded operator function, I should say. Now this return statement implicitly uses the shared pointer constructor of the query instance, and so we can think of this as being passed to the query constructor with a shared pointer, the interface of which is a shared pointer to a query base. We'll name it X for the sake of argument. Okay, here's the general idea. Let's graph this out. As a consequence of the evaluation of this entire expression, again taking into consideration this final step, we essentially obtain a query object. Let me just double check this just to make sure. Okay. We essentially obtain a query object, the representation of which points to an OR query. And the OR query is derived from binary query, which maintains a state, and that state relates to two query instances which in and of themselves have Q data members that point to dynamically allocated objects of types in the inheritance hierarchy. And so we refer to those as the operands. One of the operands essentially points to an AND query instance, and we'll just name that Q as in query. And the other operand points to a word query. We'll name that Q. Furthermore, this maintains state and points to two operands. And in this instance, the operands are word query. We'll just write word Q to be succinct, and word Q, and these are represented in query instances. Now here's the point to understand. Whenever we write something like, suppose that the query object constructed is called Q, and we call eval on it, passing text. What's going to happen? Again, we can go through the implementation systematically to determine precisely what's going to happen. But essentially what's going to happen is we're going to call eval on this top level query instance, and that's going to call eval on the object to which the Q pointer refers. In other words, that Q pointer refers to an OR query instance, and it's going to call eval on that. And the implementation of the eval function specified for OR query calls the eval on its operands. And so consequently, it's going to call eval on its left-hand operand, which in this instance is a query instance pointing to an AND query. And the AND query in turn is going to call eval on its operands. In this case, they're word queries. And what's going to happen ultimately here is it's going to execute the logic that returns the intersection of two given words and return a query result. And that query result is passed back up to this level here to the OR query instance. And the OR query then calls eval on its right-hand operand, which in this instance is a word query. And in that case, it's just going to return every single line that the word appears on, represented as a word query, as a query result instance. And so consequently, we obtain a situation whereby we have a query result here, conceptually, which represents the intersection of two words at this lower level. And we have another query result which relates to every single line that a particular word represented by this lower level word query was found. Now the OR query in and of itself applies its own logic. So it then finds the union of these two particular query results, and it passes it back up through the various different calls to eval. So in other words, at this level, it's going to return to the non-virtual call to rep a query result that represents the union of the results, and then that in turn is going to return a query result to the site of the call. And then what we can do is we can initialize, by means of automatic type deduction, a certain variable with that return type to capture the query result that represents the result of the query. And in that way, we essentially obtain a query result, by the way, the representation of which, the string representation of which, consists of a combination of the string representation for this and the string representation for this combined up here to form the string representation of this. Because remember, the binary query interface specifies that rep combine the string representations of its operands, and so consequently we're going to obtain something like, just to be general, word 1 and word 2, and I don't know if it parenthesizes it like this, but we're going to obtain something like this in terms of the actual string representation. So whenever we look in the query result and print its contents, it's going to print a string corresponding to that. We're then able to print the line numbers that relate to the particular query operation, and then we also print each line that it occurred on, and we'd already discussed that implementation in our early implementation. So in that way, as I have said before, again, we could go through the implementation. If you really need help, if anybody's watching this and they need help, just comment below and I can help. But in that way, what we have achieved is quite remarkable. In other words, in my view, it would be, in terms of the specification where I took this example from, it overloaded I haven't really considered this in great detail, and so consequently I don't know if it would even make sense or work. But the overloaded operator for the query instance the overloaded output operator for the query class type just printed a string representation that represents the kind of query that particular query instance represents. But I think it would be possible to potentially define the output operator such that it automated the process of printing the results of this particular expression here. So in other words, we would basically specify a particular query instance with this notation here, and then write something like cout. But here's the problem. That's why it's not possible. There's no way to specify tq unless we define some systematic or ingenious mechanism like the use of a global variable or something. So that's why we have to use that notation. But I suppose what we have to take into consideration here is that we've already defined a print operator for the query result class. And so consequently we can take if we specify the declaration of a variable here, initialize with the result of that, I can't remember the precise interface, but we could write something like this. And that way we could print the results. So basically what we've done here is we have satisfied our initial requirement that we devise the appropriate implementation that performs the necessary operations to evaluate complex queries, the notation corresponding to which is specified by the client user of the library in a manner similar to the following. And they write something like the following, and they write something like the following to acquire the or to obtain the query result, and they write a print function invocation to print the results. This and these 3 lines of code all work because of that complex implementation details that we implemented before. And I already hinted at this before, but this relates to the expressive power of the C++ language. It is immense. And I will talk about this in particular when I discuss a matrix implementation, which is relatively complex. It enables us to automate certain processes and so on and so forth using specialized member functions in order to execute essential services to maintain the appropriate representation and so on. And essentially what we end up with is a situation whereby, for instance, in the matrix case, we can declare a matrix with a notation, this isn't precisely what it is, matrix M, and initialize it with some representation. And by the way, the matrix implementation is dynamic in the sense that it can automatically adjust to various different representations we may supply. And suppose we declare another matrix called Y, we'll call that X. And then we can say something like Y multiplied by X, and that's all we need to do. And the expressive power of the C++ language hides all the complexities in these fundamental operations in abstractions that encapsulate that complexity. But anyways, I'm getting a bit ahead of myself. We'll get to that point when we get to that point. But before I end the video, I would like to discuss how we got to this point. So I'm going to stop the recording just to review the material, and then we'll continue. Okay, so the last thing I would like to do is just outline some of the basic ideas that led to the development of this implementation. And so here's what I would propose. At the beginning of this, we started off with a basic implementation of TextQuery and query result that enabled us to perform relatively trivial operations. And whenever we considered extending the query system, one may think that it would be appropriate to one may think it would be appropriate to take the TextQuery class and derive other classes from that class to represent specific kinds of queries. Now, I haven't given much thought to this, but that approach would perhaps not yield there would have to be a solution to the problem, but it wouldn't necessarily be as easy to implement a solution that gave you the expressive power of this particular implementation. And before I proceed, I just have to say this program is a pretty robust, solid little program. It's relatively simple, yet it's relatively complex. So if you're struggling to understand it, don't worry, because it is relatively complex, but at the same time it's relatively simple. That doesn't make any sense. Anyways, doesn't matter. Now here's the problem. That design philosophy wouldn't make sense because of the fact that a not query is a kind of query. Let me just review this. Okay, so essentially, in relation to a not query, in order to for a not query to be a kind of word query, we would essentially have to identify the word for which the not query was searching. And there is essentially no word that correlates to that notion. And so in terms of what the not query represents, it represents a word query that negates it represents a word query or any other kind of query whose value it negates. And in relation to the AND query and OR query abstractions, they are queries whose results it combines. And so those considerations lead to the conclusion that we model the different kinds of queries as independent classes that share a common base class. And so that's how we get to the point where we conceptualize about this notion of defining this abstract base class from which we derive specific kinds of queries that encapsulate the logic performed in order to provide the semantics of an AND query and an OR query and so on and so forth. Now, to be succinct, this is a representation of the inheritance hierarchy. We have a query base at the root of it, and we inherit word query, not query. But then we have this further abstract base class called binary query, and this is a direct representation of the inheritance hierarchy we implemented throughout this lesson. And that in turn AND query derives from binary query, and OR query derives from binary query. So what we have done here is we have essentially constructed a relatively complex class hierarchy that represents our query system. And here's the problem. Whenever we want to develop a library for end users to employ, we want it to be as simple as possible, and so consequently what we want to do is define an interface class. And query is precisely that interface class for all the reasons that we've outlined previously. So query is an interface class that enables us to interact with this complex inheritance hierarchy such that end users can construct relatively complex queries with notational convenience. In other words, they don't have to mess around with different names and so on, and they can get desirable results as a consequence of that. So that's pretty much it for today's lesson. It was a long lesson, I understand that, but it was a relatively complex, certainly more complex than the previous example, which was extremely trivial. And I suppose what I would say is that we started off with a simple implementation. We wanted to extend it with the aim to enable evaluation of complex queries formed with relatively simple notation, and we consequently proceeded to implement that. And then we walked through the implementation in terms of how it works with a concrete example, and we finally discussed in relatively little detail, but a sufficient amount of detail, the diagrams relating to the inheritance hierarchy we employed. So that's the end of today's lesson. It was a long lesson, I understand that. If you don't like these, then do comment, and I'll perhaps see if I can change it for the future, but I prefer these longer lessons because it's verbose and it talks through precisely what's happening. So with that being said, thanks for watching today's lesson. I'll see you in the next lesson.